All right. Ladies and gentlemen, good morning, good afternoon, good evening. Depends where you are in the world. Tom, thanks so much for joining us right now. And welcome everyone to the 2021 Summit on Drone Geophysics. This is the second, hopefully, annual event after a very successful event last November in 2020. I'd like to thank all the sponsors today. We're not going to list them, but they are on the program itself. My name's Jan Franke. I'm actually the second chair today. I'm with Geolytics. My background is in ground penetrating radar, and I work quite a bit with GPR on drones. Kian Dawson is with the United States Geological Survey. He is the lead chair today, and he will be coming back online in a moment. So just to give you a quick overview of how the day will run, we have a number of presentations. They're each given about 15 minutes. There'll be a warning for each one at 14 minutes to wrap up the presentations, and then we'll have a scheduled 5 minutes of question and answers. During the presentations today, everyone will be muted, so we would like you to ask your questions in the question answer box, and we will get to all of your questions, or hopefully all of your questions. Today is the last day of this 4-day conference, and because of that, at the end of the presentations, we will be running a little bit of a discussion about the conference in general, where you'd like to see it go next year, and revisit some topics that perhaps weren't covered fully in the previous 3 days. So we'd really like everyone to stick around and be part of that interactive discussion at the end of the last presentation. It is a great pleasure to introduce a man synonymous. In fact, I think in the dictionary under UAV geophysics, it says see him. He's got 40 years of experience, which is something that most of us can't even touch. Applying all sorts of geophysics to mineral exploration activities for the most part, I think, but also some geotechnical and environmental studies. Since 2017, he started working with the mag arrow from Geometrics. It's a very lightweight magnetometer designed for drone use. And in the intervening 3 or 4 years, he's done more than 50 UAV projects for low altitude aeromagnetic surveying. And he's done everything from geothermals to hydrocarbon mapping old oil and gas wells, pipelines, all sorts of things. So without further ado, I would very much like to, it's an honor to present Ron Bell. Ron, take it away.
Thank you very much. Can you, is my microphone on? Can you hear me?
It is.
Yes.
Yes. Okay. Thank you. The reason I asked that, Jan, is I've got this screen thing going and I just don't see anything else but my slide presentation. Anyway, thank you everybody for showing up for my presentation. It's titled UAS-enabled gamma ray mapping at the Scheartzwalder mine, Jefferson County, Colorado. My name is Ron Bell. I'm a pretty senior geophysicist, but these days I think of myself as the only living geodronologist on the planet Earth. And of course, that is my own opinion. So today I'm going to talk about a little bit about what I define as drone geoscience. And in the DG measurement space, I'm going to speak a little bit about mapping beyond visual line of sight, ultra low altitude UAV surveys, and then I'm going to talk a little bit about MagArrow, the EM61 light, and the GEM2, because in fact, all of this kind of figures into doing what I call ultra low altitude UAV surveys and some of the developments and the work I've been doing trying to improve the data quality. Then I'm going to quickly get into the gamma ray spectrometer that I've been testing, a little bit on the Scheartzwalder mine, and talk about, show some of the results and discuss a bit of the lessons learned and talk a little bit about the next phase. And then at the very end, I'm going to talk about a new initiative that I'm currently proceeding with. All right. Anyway, I'll quickly go through where I was at. That's the what I'm going to talk about today on that slide. This is the Back again to what I call drone geoscience. Remote sensing is everything that tends to be sensing things that are on the surface, and geophysics, of course, tends to be things that are below the surface. The photo at the right was a part. I was of a mag arrow survey using a perimeter 8. I did that. I was participating with helping out in this. It was in Nashville, Tennessee. And it's unusual in that the idea of the mag arrow survey or the magnetic survey was to actually locate automobiles that got driven into the Cumberland River in Nashville, Tennessee. So in a sense, remote sensing and geophysics are all the same thing, whether you want to think of them as remote sensing or as geophysics. I like making that point. But as I have been working with it, I've realized that there are 3 different sort of altitudes that we tend to work in, and when we do geophysical measurements with drones or remote sensing measurements with drones. And one is the what I call the standard altitude, which I define as being from about the top of the trees, which in a lot of the places I've worked is about 30 meters, to where the regulatory airspace limit is, the ceiling of it. That's about 120 meters in the US at least. And then there's what I call low altitude, which I'm defining as being about 5 meters to about 30 meters. And but that just depended on what the local vertical structures are. And then there's ultra low altitude, which is where I'm going to focus on today. And that's really from I've sort of quasi-defined it as about 0.5 meter AGL to about 5 meter AGL. And I'm throwing this out there to get folks' opinion about should we use this kind of lexicon when we're talking about drone geophysical measurements. So then as I was putting this together, there's been a lot of talk in the drone space about what's called beyond visual line of sight. It occurred to me that most of what we do with geophysical measurements is beyond visual line of sight. And I thought, well, what kind of depth of exploration are we really looking at? And magnetics, as everybody that's familiar with it knows, it goes from about 1 meter to about very much the surface of the Earth to thousands of meters into it. And then there's the EM systems I've been working with. I haven't worked with a GPR system, but I have been working with a metal detector, conductivity meter, and I'm hopefully in the months to come, we'll be working with a semi-airborne EM system. And those are roughly the kinds of depths of penetration that we'll be working with. So what do I mean by ultra low? It's very low, but there's several things that you have to be concerned with. And one of them is, can you get your drone and sensor to actually track the Earth at a good altitude? The answer is yes. Currently, we do it by using a combination of high definition DEMs and radar altimeter. I haven't played with it yet, but some folks are using laser altimeters and some folks are using sonars. So terrain following is a really big part of the process of collecting good quality data at ultra low altitudes. Another part of the process is precise UAV navigation. And currently I'm not actually using an RTK GPS, but there are drones that I've worked with or have been part of the teams that I've worked with them that do have that on board. And I think the combination of both radar altimeters and RTK GPS is a really good, solid technical combination. Now, the other thing that has occurred to us as we've been doing these surveys is the problem of obstacle avoidance. And today we currently have a human observer. Partly that's because we have no other sensors on our drones to actually identify things that it's potentially running into. But in the future, we expect that there'll be sonars or laser style sensors that'll be fitted to the drones, or drones will actually come that way. and also fitted to the sensor, because in many cases we're actually slinging the sensor or the payload quite a ways below the actual where the drone is, and it's where the sensor is that we get concerned about. So currently I'm using a Matrice 600 Pro. For those who know, that this is a drone that DJI makes and has no longer makes, so it's kind of an orphaned system at this point. And we also use a thing called Universal Ground Control Station. It's made by a company in Latvia called SVH Engineering, and they provide the true terrain following algorithms or software and the radar altimeter. Now, the things that I wanted to demonstrate, to talk about on this slide are the things we have to be concerned about, of course, is the cost of the UAV and the sensor package. The flyability of the UAV, the payload capacity of it, the amount of flight time we get, the navigation, and the safety that's associated with that particular aircraft, and the payload stability, and the UAS noise. And the bottom two are things that I've actually been dedicating this year to working on. So what I've been trying to do or working on is developing a system that I could maintain consistent altitude of the UAV and the sensor. We have achieved that with the true terrain following and UGCS and the radar altimeter. And then I've been working on reducing sensor movement. And the approach I've been taking is trying to dampen the actual movement of our suspension system. Then I've been working on testing out, configuring and testing new sensors, and then evaluating various UAV platforms. And then ultimately, this is leading to developing commercially viable solutions. So this is an example of a data set that I acquired this year. I was hired to locate a legacy oil and gas well. I did it on the ground. It was a single well, and sometimes it's just a little bit more effective just to do a ground survey. And then I realized that when I collected the data that I actually was mapping a pipeline, which is a big issue here in Colorado. And so it's become a test site for me for bringing various tools to. And one of them I went back with and flew a very high definition mag survey with our stabilized sensor system, our suspension system that we built for the mag arrow. And those other two images are of the mag data, and superimposed on the TMI data at the very top are the flight path lines. So I flew a very high density survey, not something that I normally would have done, but I also flew it pretty low, which informed me that low and high density does have a real benefit for certain targets. Then we came back in a little later in the year, and we actually flew that same site with an EM61 Lite, which is a sensor system that's made by Geonyx Limited. It took us a while to get it up and flying. It is a heavy system, and our drone, when we first launched it, really complained about it. We spent quite a bit of time reducing the weight of it. And then these data that you see on this screen are from that pipeline that we had acquired in the, this is the mag response of that pipeline. And there's the EM61 response of that pipeline. And you can see it has 4 channels, and we mapped it, we nailed it. So, and second system that EM system I've been working with is called the GEM 2, and those that know about it will know that it's really more of a conductivity mapping system. I've actually flown it over that same test site, but I don't have that data prepared to show. But one of the things we have been working with is we've been trying to figure out what level or how close to the drone we can fly it. The picture on the right is when we first started out working with the system, we flew it at about the level we were flying the mag arrow at the time. The photo in the middle is from March of this year, where we actually flew it much closer to the drone. And then it wasn't because of the noise of the drone, it was more because of stabilization and how to when you have a semi-rigid suspension system. We then modified it with a stabilizer in the center. You can see that. And that actually is sort of a work in progress, but it actually improved the data quality. I'm going to back up a minute here and show you that you can see that in the EM61, this right here, that middle, what looks like a stabilizer in our other systems, that's actually a bucking coil. And that gave me the idea of actually start applying that technology or that approach to stabilizing.
If you can start to wrap up, that would be great.
Oh, I got to wrap up. Wow.
You're over the 15 minutes. Yeah, thanks.
Okay. Well, I'm going to get into the Scheartzwalder. If anybody wants my slide presentation, I'll be happy to email it to them. This is what we were doing with the D230A was really just trying to test to see how it was going to fly. We happened to, one of the big questions was, where do we go and test it? This happens to be about 5 miles north of Golden. And you can see by this photo here, the terrain is pretty steep. But mostly I want to point out that the terrain where they were doing the remedial action was really highly variable. We showed up, I then planned it. We flew a quick survey. This is the total count data. This is the potassium, thorium, and then uranium. What we learned was, this is a slide that tells you about the lessons learned. One of the things that I had to do at this site was there was a lot of vertical power lines across it. I had to fly it high above that. And I hadn't had enough experience with the radar altimeter. I didn't feel comfortable flying it really close to the ground. So I elected not to do that. These are the things we're going to do this coming year. Locate the, anyway, I'll let you all read that. Now, this is an initiative I wanted to make everybody aware of that I'm working on, is actually developing a test site. One of the problems that I've had in the Front Range here is that a lot of the places I test, when I identify like a pipeline I want to go back to, they actually will remove those things. They're going to become residential developments. So I'm looking to develop a test site that anybody can go use, and I think I've located one. If you all are interested in helping me get it established, just drop me an email and we'll continue the conversation. I'm ready to take questions now, if you have any questions.
Thanks so much, Ron. That was great. I'm afraid we don't really have much time for questions, so we'll have to save those to our middle discussion after all the presentations.
Okay,
so
fair enough.
But if anybody has any burning questions before then. So we will be transitioning to our next speaker. Stephen Vanderveek will be speaking on radon corrections for UAV-borne gamma ray measurements. And I think Lori will be sharing their pre-recorded presentation. And we do have some of their colleagues and co-authors on the line, Han Limberg, to answer questions after. So take it away, Lori.
Welcome to this presentation, in which I will discuss how to apply radon corrections for UAV-borne gamma ray spectrometer studies. Everybody that's familiar with geophysical gamma ray measurements knows that radon can be an issue in outdoor measurements. In this presentation, I will discuss the issue of radon and propose 2 new methods that make it possible to correct for radon in UAV-borne gamma ray measurements. My name is Steven van der Veeke. I'm an R&D engineer at Medusa Radiometrics, a company that specializes in the production of gamma ray spectrometers and the software tools needed to analyze the radiometric data. I combine this position with a PhD at the University of Groningen, and the main research topic of this PhD is gamma ray spectrometers on UAVs. And this topic makes this conference very applicable to the research I'm doing. When I started 4 years ago, the use of the relatively heavy gamma ray spectrometers on UAVs was very new and not a lot of research was done with it, simply because it was not possible yet. And I'm very thrilled to see that we moved out of this stage with gamma ray spectrometers on UAVs and that it is a technique that's now being routinely applied. What remains are the analysis methods for processing data, and this is the topic of this presentation. The first relevant question for the application of this research is, why would you want to use gamma ray spectrometers to investigate the soil? Well, a gamma ray spectrometer measures radiation emitted by the decay of the natural occurring radionuclides, potassium, uranium, and thorium. These radionuclides tell something about the composition of the soil. In fact, this signal is so unique that it translates to something we call the fingerprint. We know that each soil is a complex mixture of different minerals. Among these minerals are the tiny concentrations of the naturally occurring radioactive elements, potassium, uranium, and thorium. These are the elements that we can measure in the field and in the lab with the gamma ray spectrometer. The fingerprint of the soil is the idea that the concentrations and ratios of these radionuclides is unique for each sediment composition, and therefore each soil. And thus we can establish a relation between the soil parameter and something we measure with the gamma ray spectrometer. As an example, water contains no radionuclides. Therefore, water does not have a gamma ray signal. Sand contains some traces of radionuclides, and therefore we can measure the concentration of potassium, uranium, and thorium, which are usually low in sand. Clay, on the other hand, generally has a larger concentration of radionuclides, and therefore we can make the distinction between clay and sandy soils. Now, I'm going to expand this example with a typical soil survey. The first step of gamma ray measurement is to map an area with a gamma ray spectrometer mounted on a vehicle such as a quad or a UAV. A large area can be mapped by driving or flying in this area with this vehicle. The map you see in the slide has dimensions of 50 by 50 kilometers and was captured only in a couple of days. Then the second step is to take soil samples. These samples are analyzed in the lab and the parameter of interest, in this case the clay fraction, was correlated to a parameter we can measure, in this case the thorium concentration. And as you can see, there's a good correlation between these quantities, and therefore this relation can be used to make very detailed maps of the clay concentration of the whole area. Note that this specific example has clay as the soil parameter of interest. But this technique has also been used to map other soil parameters, such as sand content, organic matter, pollution, such as PCBs or PAXes, and other soil parameters that have a correlation with a radionuclide that can be measured with a gamma ray spectrometer. Now, the next question is, why use UAVs? The technique is commonly applied with ground-based vehicle or airborne vehicles. What's wrong with them? Well, to start with the airborne platform of an airplane or helicopter. These are generally quite expensive, plus you need very large spectrometer systems to overcome the attenuation due to the high flying height. So this is expensive, not easy to set up, and generally only used to characterize very large areas. Now, the ground-borne vehicles can have a much smaller spectrometer and still capture a very high resolution because they are close to the ground. However, as you can see, sometimes this is not the preferred platform. So to conclude, UAVs have the unique combination of advantageous properties to map an area with a very high resolution, like the ground-borne measurements, but at the same time, UAVs have the possibility to fly over difficult accessible terrains. This can be wet terrains, as shown in the picture, but of course, this can also be very rocky or even radioactive polluted terrains. The current state of technology, among which the UV technology and the spectrometer technology, allows the routinely use of this measurement setup for geophysical measurements. To give a few examples, this platform is used in agricultural settings, in environmental pollution mapping, and in the mapping of mine tailings. All these measurements were done with relatively big spectrometers, ranging from 350 milliliters up to 2 liters of cesium iodine crystals. The spectrometer technology is in such a state that off-the-shelf spectrometers developed by Medusa can be strapped under an UV and used for the measurements. So, the spectrometer technology for UAV-borne measurements is there, but how about the analysis methods? The first important concept is the footprint and height corrections. The footprint is the volume of the soil that's emitting gamma rays that end up in the spectrometer. This is a very important concept when designing your survey and determining the UV measurement height. And it is very important in the analysis because it will tell you something about the maximal spatial resolution that can be achieved when doing the measurement at a certain height. A concept connected to this footprint are the height corrections. Gamma rays that travel through the air are attenuated. This attenuation of gamma rays has been described for airborne measurements with an aeroplane. However, for UAV-borne applications, this attenuation is significantly different and therefore different corrections need to be applied to end up with correct absolute radionuclide concentrations in the soil. Both these concepts have been described in a paper published in the Journal of Environmental Radioactivity, and this is published open access, so available to anyone. The second theoretical concept in UAV-borne gamma ray measurements is the question of how low can you go in terms of spectrometer size. Under an UV, you want to have the smallest and lightest spectrometer possible, while still maintaining the ability to capture the spatial variation of the radionuclides while doing the survey at an acceptable speed. For this, we have published an article that describes a comparison of 3 different detector sizes: a 350 milliliter, a 1 liter and 2 liter cesium iodine gamma ray spectrometer mounted simultaneously on a UAV. The conclusion of this article: in many situations you can use a very small detector when you do smart data processing and make sure that your survey parameters are optimized for the detector size. And now the main topic of this presentation. The next topic in UAV-borne gamma ray measurement analysis: radon corrections. Radon is a radioactive gas that can migrate from other areas into the area where you are measuring. This radon gas emits gamma rays that end up in the detector, and therefore giving you a wrong reflection of the radionuclide concentration in the ground. So, where does this radon come from? The decay chain on the slide is the decay chain of uranium, commonly found in the ground, and the radionuclide that we want to map. Normally, you would measure a gamma ray spectrum that's the response of all the gamma rays emitted in the decay chain, assumed to be in equilibrium. But if we look closely to the decay chain, we can see that it contains radon. Radon is a gas with a half-life of 3.8 days, and these properties allow radon to escape from the soil and migrate to other areas, influencing our gamma ray measurements. Now, the part of the uranium decay chain before radon contains only a small fraction of the gamma rays emitted by the whole decay chain. In fact, the larger part of the already minimal contribution are very low energy gamma rays that cannot be accurately captured by a cesium iodine gamma ray spectrometer. And if we take a closer look at the spectra resulting from radon and from uranium, we observe that these are almost identical. So we can conclude that only using spectral analysis, it is not possible to separate uranium from radon. In classical airborne gamma ray spectrometry, there are a couple of options for radon corrections. For instance, the use of spectral ratio method, looking at the ratio between 2 prominent peaks, or using a separate upward-looking detector that's shielded from below and therefore only captures radiation emitted from the radon above your measurement system. But both methods will not work in UAV-borne applications. A separate detector is too heavy to add to your platform, and the spectral ratio method relies on the large separation between the ground and the detector, which is commonly present in airborne measurements when using an aeroplane. And UAVs, you want to fly as close as possible to the ground, and therefore both methods are not an option. The first new method we propose has to do with the geometry of the measurement. Radon is located in a cloud around the detector. Uranium is located in the ground. So when doing measurements at several heights, starting from the ground, we can establish the following relations. So let's start with uranium in the ground. When the detector is on the ground, it will measure gamma rays directly coming from the ground. Now, if the detector moves away from the ground, the gamma rays emitted from the ground will be attenuated by the extra layer of air between the ground and the spectrometer. Thus, the uranium signal from the ground decreases with measurement height. But the radon signal has a different behavior. On the ground, it will measure gamma rays coming from a half-infinite sphere of radon above the detector. When moving away from the ground, the radon signal increases because of the extra layer of radon-filled air between the detector and the ground. Therefore, the radon signal from around the detector will increase with measurement height. And this is shown in the graph on the bottom left. Radon increases with height, uranium decreases with height. Therefore, measurement at a fixed height interval can be used to establish if there's an influence of radon, and it is even possible to separate the radon by fitting these curves to your measurement data. The only limitation of this technique is that you need to do additional measurements at the beginning and possible at the end of the survey to establish this height dependent relation. Now, for the second radon correction method, we propose a new detector design. The second new method we propose is a variation to the upward-looking detector. This requires a change in the hardware of the detector. The scintillation crystal needs to be split in half, and a signal from each half has to be recorded separately. Looking at the ratio of counts in the top and bottom half allows the possibility to distinguish the direction of the gamma rays. Gamma rays from the soil mostly come from below, and therefore have a slightly higher count rate in the bottom part than in the top part of the detector. For gamma rays emitted by radon around the detector, those are mostly emitted from above the detector. And this will result in a slightly elevated count rate in the top part of the detector. Although the differences in count rate per detector half are small, it is significant. And if you have enough measurement data, which is usually the case in surveys, you can establish the presence of radon and even estimate the radon concentration. The combined signal of both detector halves is used in the gamma ray analysis of potassium, uranium, and thorium from the ground. So this configuration of upward-looking detector that's embedded inside the detector does not decrease the yield of the survey. And it is a new way to separate from radon from uranium, which is not only applicable for UAV-borne measurements, but for ground-borne measurements as well. And this brings me to my final slide, in which I want to conclude. UAV-borne gamma ray measurements have some distinct advantages. They can fly over inaccessible terrains while still maintaining a high resolution. And the technology of both UAVs and gamma ray spectrometers reached a mature state that they can be routinely used in gamma ray surveys. However, I want to make the case that active research is needed for the further interpretation of gamma ray data in UAV-borne applications. Height corrections, choice of detector, and radon corrections have been developed. However, there are still topics that need additional research. For instance, how to apply cosmic corrections, how to process data coming from point sources, and how to incorporate complex geometries such as canyonings of mining pits, just to name a few. Therefore, input from the geophysical community is needed. And with this, I would like to end my presentation. Thank you for your attention, and if you have any questions, feel free to ask them or contact me later.
Great, thank you so much for that. That was a great recording of talk, and I believe Han Lindberg is here one of the co-authors, to answer any questions. So Han, one question we did have is, maybe once we're done with the Q&A, if you can drop the reference of the article mentioned into the Q&A chat, that would be great.
Sure. I'll just drop them right away. Okay. So let me see. Yeah, we'll do that in a second. As mentioned, I'm a colleague of Stephen, and I'm actually partly guiding the PhD research that he's doing. Stephen is traveling at the moment, so it was difficult for him to join live in the meeting. So, but I'm going to be here, and if you have any questions, or you can ask them now, or maybe later in the discussion after this session.
We have another question in the Q&A, Han. Did Stephen mention the units sensor are available commercially or off the shelf currently?
Sorry, could you repeat that? Whether the sensor is off the shelf available, or?
Yes, is the sensor commercially available right now?
Oh yeah, sure. Yeah, yeah. Actually, we've been working on three different types, which are technically the same systems, but they differ in weight, basically in the size of the crystal used. And there's a small one, which is a 3x3 inch detector, which is about somewhat less than 3 kilograms, which is nicely fitted, for instance, for use on this M600 drone. And the largest one that we've been testing with is an MS2000, which is a 2-liter system. But then you already go to about 10 or 11 kilograms, which is for many drones beyond their capabilities. But there's different options.
Great, thanks. Other questions? Folks, panelists can't enter into the Q&A, so you're welcome to just unmute yourself and pop in.
Okay. I see there's a question from Johannes Stoll, I think. Maybe you could say something about that. I'm trying to figure out what he...
That was the request for the reference mentioned in the talk.
Okay, sorry.
So another question, sorry, in the chat, you're right. What is the recommended volume and weight of the scintillator?
That strongly depends on the application, which is kind of a yeah, sorry answer, so to say, but what we basically see, what as a good trade-off on the one hand between available drones and payload, and the other hand to maximize the volume of the detector, we would suggest to go to at least for most of the applications to 700 milliliter to 1 liter of volume, and that's also in one of the papers that Stephen was mentioning. There is a comparison between these different volumes, and of course, again, it depends on the application. If you expect, for instance, if you're doing a survey on a old mine dump, or locations where you expect pretty high levels of radioactivity, of course you can work with a small crystal. But for generic mapping, for instance, what we've been doing a lot is mapping crop fields, for instance. Yeah, it's better to have to start at least a 700 milliliter crystal type. And then you talk about typical weights of about, say, 4.7 kilograms for an MS700, up to almost 7 kilograms for a 1 liter system.
Great, thanks. Any other questions for Han? Well, folks, think of them later. You can drop them in the Q&A, and also we'll have some time in the discussion after all the presentations to circle back once things have had a chance to percolate. So thanks so much, Con, for stepping in and fielding the Q&A. I appreciate that.
Sure.
So with that, we'll move on to our next speaker. Storm Weiner will be speaking to us about gravity radiometry with a portable cold atom interferometer. So Storm, if you want to go into full screen mode. Yeah.
Okay. Is that working now? Can I start?
Looks great. Go for it.
Okay, so yeah, I'm going to talk about my project, which we're at UC Berkeley. We're building a gravity gradiometer, and an outline for the talk. So the gravimeter is not complete, so I'm going to talk about the principle of operation and update the progress on this gradiometer. So first, I'm going to explain how atom interferometry works compared to a common laser gravimeter that some of you might be familiar with. Then I'm going to describe an absolute gravimeter that we recently decommissioned that we built in our group, and then talk about the progress on the next iteration of this, which is a gradiometer, and it will be mounted in an airborne platform. So the basic principle of a laser interferometer is to take a laser source, split it, and then recombine it and measure the interference. And the interference is due to any sort of difference in propagation between the two arms of the interferometer. And that difference, that phase difference, can be due to either a path length difference or refractive index variance if you put some object in the path of propagation or anything like that. And that phase difference translates to an intensity difference in the two output ports here. This is a common configuration for many different kinds of sensors. And in particular, the FG5 absolute gravimeter from Micro G Lacoste uses this principle where they have a vacuum chamber, and inside that vacuum chamber, they have a test mass, which is one of the mirrors of the interferometer. And by dropping that mirror, they change the path length and measure the interference fringes on this detector. And by measuring those interference fringes, they are directly measuring the trajectory of a free-falling object. And from that, they can reconstruct the gravity measurement. In an atom interferometer, the roles of light and matter are inverted. And what I mean by that is the wave that we're interfering is made of matter, and the mirrors and beam splitters are made of laser pulses. So it's like a direct complement. And in this diagram here, what we see, these numbers 3s and 4s represent the internal states of the atoms. In our case, they're cesium atoms. And the P's and H bar K's represent the external states of the atom, namely the momentum states. And in this case, we have a near resonant laser light that splits the atomic wave function into two paths. And in the process, this absorption process couples momentum into the atoms, which causes a physical separation as well as this internal state difference. We have a mirror to reflect the paths, and then another splitter, which we combined the matter waves. And in this process, the phase difference between these two paths gets mapped into a population difference in the two output ports, similar to the intensity difference in the laser interferometer. And by measuring the final populations of these two atomic states, we can reconstruct the phase difference between these two paths. And in this interferometer configuration, that phase difference is directly proportional to the gravity. In particular, it's the projection of the laser K vector onto the gravity direction. And the timing between the pulse, increasing that timing also increases the sensitivity of this measurement. So this is a photo of our gravimeter. We called it Mini G because it's so small. Somewhere on the order of 100 million cesium atoms comprise the test mass. And the phase difference is due to the gravitational potential difference along those two arms of the interferometer. And there is no direct trajectory measurement. All we measure is this final output phase. We don't measure the phase as it falls. We measure the phase right at the end. And yeah, that's the principle of operation. And I want to thank Dan Shire and Jeff Phelps at USGS for helping us perform these measurements and compare our measurements with conventional gravimeters as well. So the important thing about this geometry here is that we have a laser beam coming down, and we use these pyramid reflectors so that the light is coming in from all directions onto the atoms, and that's what prepares the initial state of the atoms. It cools from a background vapor into a small cloud, and that small cloud is then dropped, and the laser pulses interrogate the atoms as they drop, and then when they pass in front of a photodetector, then we send a series of imaging pulses to measure the populations in the two different internal states of the atom. And we detect it over here, and from that detection, we extract the phase. And I want to mention that Muquans is a company that actually offers this kind of gravimeter as a commercial off-the-shelf product now. It's the only one, to my knowledge, the only commercial product using this technology. And just as a comparison between the FG5, the Muquans, and the Mini-G, you can see that the sensitivities of these atomic gravimeters is not quite as low as the FG5 yet, but it's still a developing technology, and there's room for improvement for sure. In particular, coupling more momentum into the different arms of the interferometer by using fancier laser pulses is one way to do it. So now onto the current project, which is no longer an absolute gravimeter, but a gradiometer. The idea is just to have two of these interferometers probed by the same laser beams in the same vacuum chamber, but vertically displaced by a quantity called the baseline of the gradiometer. So the vertical displacement means that if I have any vibrations in the sensor, the top and bottom interferometer will experience the same vertical vibration. So as long as we can keep symmetry between these two interferometers, the difference in phase between the two interferometers should not be sensitive to vertical vibrations. But in principle, we might still have horizontal vibrations that could cause a phase shift. And the idea there is to use a uniform laser intensity in the transverse direction to cancel that as well. So some numbers for our design. This baseline is about 1 meter. The interrogation time between our interferometry pulses will be at most 190 milliseconds. And when you work out the math for the expected loading time and atom number and laser intensity and all of that, we find that we expect the shot noise limit on our phase detection to be about 6 milliradians. And based on that shot noise limited sensitivity, we expect 5.4 to 11 etvus per root hertz. And the reason for this large difference is it depends on how much momentum we're able to couple in. And what I mean by momentum here is how many photons of these laser pulses coupled in. So here we see this 2 is a 2-photon process. That's the minimum that we can do in this kind of sequence. And the more, the better. And this scales roughly inversely with the number of photons we can couple in. So the specific design for our gravimeter is to have, in a single vacuum chamber, we will have 2 of these atom traps probed by the same pair of lasers coming in vertically through this chamber. And each of these atom traps will contain a cloud of atoms that gets dropped and then detected just like the previous gravimeter. One important improvement to our design is, instead of using that pyramid mirror to surround the laser or to surround the atoms with our laser beams, is to use this custom diffraction grading chip. And this is a technique developed at in University of Strathclyde, where basically by patterning diffraction gratings on different areas of this chip, we can have a single laser beam come in and diffract at different angles depending on the position on that chip to surround our atoms with the trapping and cooling light. And our spin on this is basically to use a quartz substrate instead of a silicon substrate, fused quartz substrate, so we can have different transparency windows so that we can have one chip up top and another chip down below, and they are rotated relative to each other so that the transparency windows on the top chip, light passes through those windows and then comes down to the second chip and then diffracts to trap the atoms. And in that way, we can have two atom traps generated with the same laser beam coming in. And this is a diagram from the Strathclyde group showing roughly how you end up with this overlapping Mott region in the center of the trap. And here's some preliminary data from making the gratings. I have an SEM, scanning electron micrograph, on the right side, showing that I have grating dimensions, roughly what I expect. And then on the left, I have AFM measurements showing that the trench depth matches what I expect it to be. And once we have all of that working in the lab, then we will mount it onto this drone that we're having developed by a company called Event 38. So we're outsourcing the drone development. It's not our specialty, but we gave them the specifications based on our calculations of what kind of vibrations and translations we can tolerate during our measurement period. And they're in the process of building this aircraft for us so we can mount our sensor onto it. So it has a sort of a double 4-rotor design. It's designed to fly between 30 minutes and 1 hour. Our sensor payload will weigh at most 50 kilograms, and this chassis will be able to carry that. And it will use optical flow and a laser rangefinder, as well as the IMUs to try to stabilize the position in flight. And as of now, the initial flight tests are happening, so that's exciting. Hopefully we get some results from that soon. And some of the specific challenges of flight that we're accomplishing here, well, the power consumption is big. In our design, the power is mostly dominated by the 3 radio frequency amplifiers that we need to generate the laser pulses exactly the way we need. And we expect that to take in total 150 watts. Everything else will probably be less than 50 watts on top of that. So we're looking at 200 watts in total. And part of the way that we're able to get the power consumption so low is our simple optical design, where we have just a single laser diode, no optical amplifiers. There's no mechanical moving parts except for one little shutter that just blocks the laser beam at times. Everything else is electronic. For size constraints, we're using the smallest optics that we can easily handle. The entire laser module will fit on a 12-inch by 12-inch breadboard. The electronics control system is based on a homemade embedded design. The idea is that commercial electronics components, they typically run on AC power and have a lot of weight that's just kind of wasted on a rectifier and generating the DC power that the components actually need. So we're kind of spinning our own for the most part to try to reduce to simplify the power delivery and allow everything to run off of the single battery. One other interesting thing we're doing is we're using an all aluminum vacuum chamber instead of stainless steel to try to reduce the weight. And the last part here is that there's obviously lots of vibrations in flight compared to doing this on a stable platform in a lab. So we had to give up the idea of making an absolute gravimeter in flight. So we're going for this gradiometer design instead. And we're using this flat top beam for the interferometry pulses to cancel the horizontal vibrations. And based on some telemetry data from smaller aircraft, we expect that we'll be able to get good measurements in flight, but it's too early to tell exactly what challenges we'll face when we start integrating our system in the real world. And yeah, thanks for your time. That's what I have to say for now.
Great, thanks so much, Storm. That was really interesting. So questions from folks? Like I said, if you're a panelist, feel free to jump in because you can't type in the Q&A, but we do already have some questions in the Q&A. So Storm, one question is, can you make full tensor measurements with this system?
Yeah, full tensor measurements, good question. No, so we're only able to measure the vertical gravity gradient using the system. And the reason for that is if you look at this phase equation, we're only sensitive to the component of gravity that's parallel to our probing lasers. And in this configuration, our probing lasers are all going to be vertical. And as far as the derivative direction, we're only sensitive to derivative directions based on the displacement of our interferometers. So there are groups, I know of one group at Stanford that made an atomic gravimeter that's sensitive to horizontal tensor components. And they do that by having horizontal laser beams. That system is a bit more complicated. It requires more optical components, more sensitive alignment, and things like that. So we're trying to go for the simplest possible design, and that's the ZZ component of the gradient tensor only.
Great, thanks. And how sensitive is your system? How sensitive your system would be to angular motions of the platform and to ambient temperature variations?
So ambient temperature variation, the dominant effect that we experience with temperature variations in the absolute gravitimeter. Let me go to one of the bonus slides for that. So in the laser system, the real key point here is to lock the laser very closely to the atomic resonance. And we do that by having a small cesium cell that we do a spectroscopy measurement on, and use that and feedback with our laser diode. And this cesium cell is sensitive to pressure, sensitive to temperature variations. The cesium pressure will vary with the temperature, and that will change the shape of our error signal that we're locking onto. So in our new design, we're going to have some temperature stabilization on this cell. And that was the dominant effect that we saw with the absolute gravimeter. So I don't know the exact sensitivity to temperature, but it's going to be predominantly due to our electronics after we fix this problem. So yeah, take that for what it is.
And I think the other part of that was sensitivity to angular motion of the platform.
I think the angular motion, yeah. So the angular sensitivity comes from this dot product of the effective laser direction with the gravity vector. So there's going to be like cosine squared or cosine term. So basically second order in angle based on the tilt.
Another question from Jeff Phelps this time is, do you get continuous measurements or do you need to hover to make a measurement?
We'll need to hover to make a measurement. So we will make a measurement about every second. And well, okay, let me correct that. We will make one drop every second, and it will take several drops to reconstruct the gradient. So, you know, we'll have to hover for, you know, about a minute to get a gradient measurement.
Great. Any other questions for Storm? Lots of excitement about seeing gravity systems come online with UAS in the chat there. So
I will say that there is a group that recently published, or I guess it's a preprint that's available through Nature on using a system like this, and they got some interesting results where, you know, they were able to basically make a tunnel detection using their gradient measurement. They got down to little under 500 atmos per root hertz. So that's kind of our competition, and we're going to try to beat that. Hopefully, theirs does not have an airborne platform. They have a ground-based platform, but the principle is working, which is encouraging.
I had a quick question about the specs of the overall system together. Does that, it flashed by, but does that bump you out of the small UAS regulations in the US? Is it large enough?
Sorry, what was the question?
What is the weight of the overall system, and is it big enough that it's bumping you out of the Part 107 small UAS category?
Okay, so I'm not very familiar with the regulations. The total weight is, you know, I think about 150 kilograms or maybe 200 kilograms, including all of the battery packs and all that. And I know that we're filing some sort of like COA exemption. I don't know exactly what number the document is, but we have, let me go to the first slide. Frank Ketchum is our aviation expert on campus, and he's taking care of all the regulations and all that for us. And you'll have to ask him. Sorry.
Oh, that answered it. One other question is, any thought on testing it on small traditional manned aircraft in addition to the UAS?
Yeah, I suppose we could. This gradiometer will be operated like on a ground-based platform, you know, for a while before we put it on any aircraft. So we could, you know, in principle, put it just about anywhere. I don't think we have any collaborators or any access to the traditional aircraft just yet. I think Jeff Phelps at some point suggested we would be able to put it on a blimp with the USGS, but we never really followed up about that post-pandemic. So maybe it's time to revisit that possibility as well.
Great, thanks so much. There's clearly lots of excitement about this. If folks have additional questions, I invite you to drop them in the Q&A or save them for our overall Q&A session. So this has been a great morning so far. We've got a 10-minute break right now, and we'll reconvene at 1:15. I do want to encourage folks to come back. I know it's Friday. We've been here for 4 days, and there's so much excitement going on. We've got great presentations after the break. And we also will have sort of a wrap up, larger conversation, not just about the presentations this morning, but talking about sort of future directions, both for this event and for our community, and ways to move forward and continue advancing drone geophysics. So take a hydration break and come back in 10 minutes. See you all there.
I can, if he's ready to go. So welcome back, everyone. I hope everyone's back with us and enjoying the session thus far. I'd like to introduce one of our platinum sponsors. You know, I've watched this industry for 30 years, and I've very rarely seen such a meteoric rise in success as Axiom. They're based in Saskatoon, Saskatchewan, up here in Canada, but have worked internationally for the last 10 years, and have really grown in the space of drone geophysics. So I'd like to introduce Pettifer from, I assume he's in Saskatoon. Please take it away.
Thank you so much, Dan. That's a beautiful introduction. With
a more focused approach, it can save an exploration program hundreds of thousands of dollars in the process. Axiom Exploration Group utilizes a cross-disciplinary integration of geology and geophysics while repurposing modern technologies from different industry sectors. We do this to create an innovative survey technology that saves our clients time and money, maximizing results, therefore increasing the success of every project. At Axiom, we've refined and perfected our approach across hundreds of projects on 6 continents. If your business is in the mining, energy, forestry, or agricultural sectors, we have the tools and experience to support every aspect of your project in the most cost-efficient way. Utilizing satellite data, detailed geomatics, subsurface geological information, coupled with machine learning and everything in between, Axiom Group has you covered. Now, where does this process start? Through the integration of our passionate in-house geologists and geophysicists, Axiom combines remote sensing techniques using synthetic aperture radar data and multispectral imaging to analyze structural trends, vegetation and alteration signatures, and ground movement patterns. We can then quickly identify complex anomalies by analyzing significant features over large areas without any seasonal restrictions. This creates a more defined area of interest for targeted terrestrial exploration and aerial geophysical data acquisition. Whether you need our diverse team of geologists, geophysicists, or environmental engineers, satellite analysis, airborne LiDAR, photogrammetry, magnetic and electromagnetic surveys, orthomosaic maps, ground penetrating radar, thermal, multi, and hyperspectral imaging. Through the use of our manned or unmanned aircrafts, with our industry-leading researchers and experts, we can provide what your project needs to succeed. We take pride in consistently delivering the confidence you need to guarantee that the goals you set in your office and promise to your shareholders are successfully and efficiently achieved in the field. Axiom is the exploration partner you can trust in all aspects of your project to ensure every chance of succeeding in the smoothest possible manner. Your success is our success.
So Axiom, it's a group of exploration that is from geology to geophysics to environmental to energy. And we've been working for the past since 2011. We've been in various places from Africa to North America to Europe. We are involved in geophysics, geology, environmental, and energy, like I said earlier. But where I'll be diving in is where I come in. I'm the senior geophysicist based here in Saskatoon, Saskatchewan, Canada. is in Canada, we do a lot of EM exploration, especially this part of the world where I live in Saskatchewan. Around Saskatchewan, we do a lot of EM for mining, uranium, base metal, copper, what have you. And one of the problems we usually have is seasonal data, like in northern Saskatchewan or in Manitoba, there are some surveys you can't do in summer, like EM grant survey. You have problem doing them in summer. So with that in mind, we started thinking of which way we can develop the technology in ground, and that's where UAV comes in, and where we have a UAV EM we are doing right now, which we have been working on for the past 2 years. We have different fleets from the 100% electric and DGMI 600 to the gas hybrid. Then we have regular A-star and fixed wing. The one I'll be diving in mostly is the UAV EM. We're trying to replace the ground EM because in Saskatchewan, we have some issues like line cutting. For you to do ground EM, go through line cutting. You need permitting. You need all that, which costs money for exploration companies, especially for the smaller ones that don't have so much money. For the bigger companies, the big names, they don't care about that. But for a smaller company that just want to do some little exploration and they don't have so much budget for geophysics, all those things add up. So we now start presenting our new UAV Axiom EM, which instead of line cutting, we just lay down our loops and we fly the lines line by line with our survey, with our system, and we get a good graph or a good response where we can now model the response using the regular Maxwell. Here is one of the response from our survey in northern Manitoba, a volcanogenic massive sulfide survey last year, and the survey is pretty aligned very well with the ground EM, which was done on that area too. And these are, like I stated there, these are the benefits of using the Axiom EM, UAV EM instead of the ground EM. We have reduced environmental costs. We cover more kilometers per day, depending on the weather. No line cutting. You can collect anytime, winter, season, fall, anywhere. And sometimes you can even go collect it, mag or LiDAR, which reduce the cost and more benefits to the company. And this is the response from our in-house software, which have been developed. You can see right here, this is a beautiful response. And these are all the benefits from having a reduced cost because technically for a ground EM, you need like 6-man crew to like a 2 or 3-man crew. The production per day increases depending on the weather. You reduce the cost, no line cutting. You can collect any time of the year, whether winter, season, or fall. And you can sometimes go collect with mag and LiDAR. And this is a beautiful response from northern Manitoba, which we did last year. The response is pretty showing very well, and the survey was good, and the result is pretty good and phenomenal. And here is one of our survey processes going on too. I don't know, I can leave my email here. You can reach me if you want more information. I didn't make so much detail because it's a 10-minute presentation. I don't want to start going into the technical or the writing, showing the software and all that. But if you need more information on what the software and what we do, you can reach me. My email, I'll put it down at the chat button and I can answer any questions you have. All right, Geoff.
Great. Thank you, Babatunde.
No problem.
Well, let's move on to our next keynote presenter, and this is an interesting subject. It's a little bit away from our traditional geophysics, but it's something that we should all be thinking about. You know, I'm absolutely impressed and excited about the dramatic growth in drone geophysics and the interest in this conference over the last couple of years. And we're all here. I mean, some of us are researchers, but we're all here for commercial reasons. Let's face it, and that's fine. We want to promote a technology. We want to put smaller sensors on smaller UAVs and fly them in swarms and do all sorts of neat things. But the part that's kind of the unmentionables, right? And in every field of science is the unmentionables. And one of the things is that we are dabbling in a space that has some regulatory restrictions and ones that are changing dramatically. There's both geographical constraints. Every country has their own rules. And even within Canada, the United States, or Australia, those rules seem to change all the time. On top of that, some of the sensors, in my field, ground penetrating radar, but perhaps radiometrics, have restrictions themselves. So we are looking at a situation of a little bit of double jeopardy, and they are unmentionables. We don't talk about them very often, but I think it's very, very important that we address that and look at that very carefully, lest we put our industry in jeopardy. So today we have the great Tom Pills from Melbourne, Australia, who deserves an award because it is currently 2:30 in the morning in Melbourne. So that in itself is impressive, and he looks awfully awake. Tom calls himself a drone lawyer, and rightly so. He is a lawyer who specializes in international drone regulations, and perhaps one of the only few of them in the world. So Tom, go ahead.
Good morning, everyone. Is my screen sharing? It looks like it is on my end.
Yep.
Thank you. Thank you for the introduction. I'll just set a timer as well. Thank you, Jan, for the introduction. As you mentioned, my name is Tom Pills, and I'm an Australian lawyer specialising in the area of drone law. And so, as Jan mentioned, a bit away from all the technicalities, the physical technicalities, the topic of our discussion today is complex drone operations flying through the regulations. And so, like all good drone operations, I'll start with a map of our journey, looking at the topics we will cover and that I'll run through in our brief time together today. So we're going to consider what drone operations are considered to be complex operations. We'll have a look at the waivers involved in permitting complex operations. We will then drill down on some more of the beast that is your concept of operations, or CONOPS. And finally, we'll look at some examples or case studies of waivers accepted by the FAA. The terminology note, as there's been a number of names attributed to drones, UAV, UAS, RPA, RPAS, and drones flown recreationally in Australia are actually legislatively defined as model aircraft. So to avoid all that, I'll simply use the term drone to refer to all sorts of unmanned aircraft, uncrewed aircraft. Let's look at topic one. Okay, so what are complex drone operations? From a legislative perspective, complex drone operations are simply operations that require a Part 107 waiver. Part 107 being the part if you're from North America. And operations that require a waiver include operations removing vehicle or aircraft, beyond visual line of sight operations requiring a visual observer where the pilot in command cannot view the drone. There's one-to-many, where more than one drone is flown simultaneously by a single pilot, and operations over people. And so a waiver is an official document issued by the FAA or your country's civil aviation authority, which approves certain operations of aircraft outside the usual limitations of the regulations. So these waivers allow the drone operators to deviate from certain rules under Part 107, or in Australia it's Part 101, by demonstrating that the operator can still fly safely using alternative methods. And so in Australia, for example, the complex operations that are most sought after are beyond visual line of sight operations, autonomous operations, and we even have remote operations where the pilot might be in another place, state, or even different country to the drone which they're operating. I want to drill down a bit more into those Part 107 waivers. And so the factors that are considered while reviewing an application for an operational waiver include things like the drone that's going to be used, the location of the operation, any unique hazards of that proposed operation, and the risk mitigations proposed by the applicant. And so the person reviewing your application from the relevant civil aviation authority will focus on your concept of operations, or CONOPS, and look at the operational hazard and risk analysis that you submit. So it's very much about providing a safety case. So the CONOPS, your concept of operations, should include a detailed description of the proposed operation, the drone itself, your operational procedures, the operational location, the limitations, hazards, risks, and risk mitigations. So a risk analysis should include the severity of each hazard's effect, the likelihood of each hazard's effect, risk mitigations, and then the predicted residual safety risk with all those mitigations in place. So the evaluator from the relevant civil aviation authority will review your CONOPS to understand that operation, the limitations and procedures. They'll look at your risk analysis, and they will consider the rationale and supporting data provided by you to substantiate how each mitigation reduces the severity or likelihood of each hazard's effect or risk to an acceptable level. It's about getting risk to an acceptable level. You're never going to remove risk entirely, but it's about getting it to that acceptable level. And the evaluator will also look at your predicted operational risk after the mitigations are applied to see what is the level of risk at which you've arrived after applying the mitigations. In North America, because Part 107 operations are performed by applicants who may not hold an air operator or air carrier certificate held by traditional aviation operators, because of that, the FAA does not accept or approve manuals in a Part 107 waiver application. However, if you do submit manuals and procedures provided in your waiver application, they are viewed positively by the evaluator during the evaluation process. So they may not be approved, but it shows that you're taking your safety case very seriously. And one operation example is, for example, a beyond visual line of sight operation can take several forms and generally refers to an operation that doesn't comply with regulation 107.31 as it's written. And so the beyond visual line of sight operation does not necessarily mean the pilot cannot see the drone for the entire operation. It includes variations of this, such as operations where there might be a physical obstruction to vision, such as a building, wall, or vegetation. And so the drone maybe remains within a distance that the operator could otherwise comply with the visual line of sight, but it's temporarily obstructed by building, vegetation, things like that. But because it does deviate from visual line of sight, a waiver is required for that type of operation. There's also beyond visual line of sight operations where the visual observer maintains compliance, but the pilot is unable to see the drone for the entire duration of the operation. So this strategy is sometimes referred to as a daisy chain visual observers, or in Australia, it's called extended visual line of sight, or EV loss, extended visual line of sight rather than BV loss, where you use an observer where the pilot in command cannot see the drone. And then finally, you've obviously got the complete visual line of sight where none of the crew can physically see the drone. And so in these beyond visual line of sight instances, the evaluator will consider how the pilot will be able to continuously determine the altitude and the movement of the drone and to ensure that it remains in the intended area of operation, and how the pilot will detect and avoid other aircraft. So there's a lot of complex and tricky aspects there. And so the evaluator, in considering that, will also look at your signal spectrum and your detect and avoid performance. So in relation to using visual observers for the daisy chain or the extended visual line of sight operations, as a waiver applicant, you should demonstrate how your observers are able to have an unobstructed view of the airspace from the surface of the ground to above the intended operational altitude throughout the proposed operational area. So what I want to do now is to drill down a little further into the CONOPS, the concept of operations, with some information adapted from a very useful organization, which you may have heard called the Joint Authorities for Rulemaking on Unmanned Systems, or JARIS, the Joint Authorities for Rulemaking of Unmanned Systems. So JARIS is a group of experts gathering regulatory expertise from 63 countries, including the United States and the European Aviation Safety Agency. They've developed some very helpful resources. I'm just going to pull something up now here. So back to the drilling further down on the concept of operations. One moment, please. So the first step is the risk assessment process, where you collect and provide the relevant technical, operational, and system information needed to assess the risk associated with the intended operation. So this CONOPS description is the foundation for all other activities and should also be as accurate and detailed as possible. It should not only describe the operation, but also give insight into the operator's operational safety culture. And developing the CONOPS can be an iterative process in that as the safety case is developed, additional mitigations and additional limitations might be identified, and that might require additional associated technical details, procedures, and other information to be provided or updated in the CONOPS. So as we've got here on the screen, at a high level, you generally collect two categories of information. operational information and technical information. So in relation to the operational information, this includes an organisation overview, such as your safety management system. You describe your staff training, your maintenance philosophy, your crew responsibilities, and how the organisation manages changes to the drone design. Point 2 of the operational information are your operations. So this is where you write about the types of operations you intend to carry out and the level or crew and any autonomous involvement. You refer to your standard operating procedures applicable to all operations for which you seek approval. Your operations will describe your abnormal and emergency operation contingency procedures and also your incident reporting procedures. Notably, just very recently in Australia, certain drone incidents are now reportable to our Australian Transport Safety Bureau, which is a body that usually accepts reports from traditional aircraft. Drones are now specifically mentioned in that legislation. So drones are certainly becoming part of the broader legislative context. There's no doubt about that. And the last point of operational information you should provide is your training, such as your processes and procedures you use to maintain competencies of your staff, your processes to recruit and qualify staff, your procedures to ensure your staff acquire and maintain currency of their skills, and any training programs you use or you've developed. As to the second point, it's in relation to the collection and presentation of the technical information. And this includes, as you can see, the first dot point is the drone description. So this is the detailed physical characteristics of the drone, including airframe, performance characteristics, propulsion system, sensors, and payload equipment. Under the drone control segment, that's your system architecture diagram of the avionics architecture, including the location of sensors, radios, redundancies. It considers your navigation system, any autopilot system, the flight control system, the pilot's control station configuration, so the remote from which the pilot will be operating, and any detect and avoid systems. Moving down, there's geofencing, so you have to describe the equipment used to perform any geofencing. Ground support equipment, so you should describe all the support equipment used on the ground, including how the drone is transported while on the ground. The C2 link, which is your command and control link. You have to provide detailed control system architecture and control links used, including your spectrum, your signal, the measures in the event of a link degradation, the conditions that trigger a link lost, and the measures used in case of a lost link. And finally, safety features. So this describes the failure modes, recovery modes, and emergency recovery capability. So finally, I now want to turn to some recently approved Part 107 waivers. And the cool thing about the FAA approvals is that they're published online. The approvals published online, whereas in Australia, they do not publish our waivers. I've made a number of freedom of information requests to the Australian Civil Aviation Safety Authority, but they've come back with redactions where they mask all the good, juicy stuff that I want to find out. So let's have a look at this next slide. Here's an actual waiver that's been approved. So look, while this is publicly available, I have redacted the party, so I'm not making an example of any particular organisation, but look at this waiver here. So this was issued a few days ago on 1 November 2021, and it's valid till 30 November. And this person obtained a waiver to operate a drone beyond the visual line of sight of the pilot, using a visual observer, not being able to see the drone, and also operations over human beings and operations over a moving vehicle. And so they've pretty much used the whole gamut. They're getting waivers on almost every single standard operating condition that typically you're not allowed to fly without waivers. And you'll see notably, the administrator found that the proposed operation can be conducted safely under that waiver because they've established adequate mitigations for risk involved with operating the drone in a manner described. And let's look at one more waiver. So this waiver was issued on 22 October 2021 and is valid until 31 October 2023. And this waiver authorises the operator to operate their drone higher than 400 feet above ground level. Again, while it's publicly available information, I redacted the operator's details. The cool thing about this is it includes the operations area. So some of you maybe identify where that is. So some closing remarks. I know we're on our way out. So look, closing remarks. So pardon me. Yeah, let me go back here. Sorry. Finally, closing remarks. So the appropriate drone is the end result after you determine exactly what you intend to do, terrain, distance, operations. So as we all know, the drone is simply a tool, and you need to determine what you're trying to achieve before deciding which tool you will use. But don't forget, no matter how complex the solution is, always be wary of the simple problem. Thank you for your attention.
Tom, let's take some questions. I think we have a couple minutes for those. Storm, you have your hand up. Storm, are you there? Okay. Any other questions for Tom, or we'll go on to our next presenter. Kian, do you want to take over on the introduction?
Sure, I'll go ahead with that. So that was a fascinating. I'm still laughing now over the horror over the toilet paper on the drone. So have to add that to my safety documents. Yeah. So Richard, if you want to go ahead and start sharing to get that set up, and I can do an introduction. So our next speaker will be Richard Fortin, who will be speaking on the application of remotely piloted aircraft systems to regional airborne geophysical mapping, a concept study. So I'm excited to hear about that. And if folks have additional questions for Tom, you can drop them in the question and answer box, and we'll circle back to those during our discussion in a little bit. With that, Richard, I pass it over to you.
Sun in my face. It's just a minute. How sunny that's a bad place. Is a visual and sound okay?
Yep, all looks great. Sounds great.
Okay, thank you. So yes, my name is Richard Fortin. It's like Richard, but pronounced French, but Richard works. I'm a geophysicist at the Geological Survey of Canada, and I will first acknowledge my co-authors. We are all but one from the airborne geophysics section at the GSC, and Alain Grenier is from our lab group. So I'll be reporting today on a small armchair project that we've been conducting, and it's related to application of remotely piloted aircraft, RPA. I'm training myself to use this word. To application to regional airborne geophysics. I'm talking large scale survey. Sorry, I'll just minimize this little screen. Okay, so the role of the airborne geophysics section at the GSC is to support our programs with airborne geophysical need. We're primarily doing aeromagnetic and gamma ray spectrometry because it's in relation to framework mapping activities, but we're doing occasional gravity and some targeted EM on occasion. All our contract, we don't have our own aircraft, so all our work is contracted to service providers. So a lot of our work is about contract supervision, QA/QC of the data, and all the data we obtain at the end is free, and we ensure public data release, and we do also occasional data analysis interpretation to support internal projects. To kind of scale the importance of airborne geophysics at the GSC, in the last 10 years, actually last 10 years finishing last year, because this year we've been down doing not much because of the pandemic, but in the last 10 years there's been $40 million Canadian dollar of public investment that was for about 60 surveys with a few contracts in excess of $1 million Canadian. So that all the data supported mapping and exploration activity at the GSC. It's a lot of money, but the return value of the programs that we run at the GSC, and not just like the airborne geophysics, but everything, have been estimated to be $7 for every dollar invested. And this is from an Ernst & Young study released in 2020. And this keeps growing because the data and all the bedrock maps we produce are still available and will be for years to come. So the last 20 years I've seen, as you all know, significant development in RPAS technologies, consistent progression of regulation toward airspace integration. And there's a large range of case studies that have been presented and trialed in the a variety of potential application have been trialed. So we wanted to evaluate the opportunities offered by this new technology to our future mapping program. As mentioned, we're conducting this small project through one of our program, the GEM program. The goal is to draft a preliminary concept of operations for using RPAS in regional airborne geophysics. This should hopefully will provide a framework for development of capabilities, identifying benefits, challenges, and technological gaps. For us personally, it will provide us with the knowledge to be able to draft technical specification in time that are practical, but primarily that ensure quality and validity of data for mapping and exploration activities. We also, as part of this project, that's the next step after the drafting the CONOPS, we also plan to survey somehow industry in some way to quantify or verify current capacity to conduct long-range BV loss survey operation. That could be done through a formal request for information on our Government of Canada procurement portal. So we'll see how this goes. There will be 3 parts to this talk. The first will be a review of current practice in airborne geophysics. And then we'll go to an account of the expectation we have and the challenges we foresee with this application. And then we'll conclude with what we have now as a draft concept of operation. Really focus more on logistics operation aspect, and that would provide some sort of preliminary vision, I guess, on intended use and the way it would be applied. Airborne geophysics has a wide end user community, but on the production side, it is a highly specialized field. It's usually not really taught in school, and it rely on a rather small and independent industry. Here we have a list of the main equipment that would be required for radiometric magnetic survey, as this is the main kind of survey conduct. With pictures of typical aircraft, so light utility aircraft usually that are used for flight operations. I'm not going to go into much detail here. I highlighted our technical specification for requirements for surveys at the GSC on our contract, and I probably should flag the weight of the radiation detector. Could be a great factor and an important factor in RPAS integration. A single pack like the one picture there is 125 kilogram, and we can easily have 2 or 3 on a survey, or we will require 2 or 3. And also the installation of the mag sensor on the originally mounted Stinger is also a requirement of our surveys. So that provides some clearance between the sensor and the sources of magnetic noise, and we prefer that over a sling or a bird. A mag sensor on a bird. To describe airborne geophysics operation, I will refer to the Gifford River survey that was flown in Nunavut by GDS Incorporated in 2017-2018. Note on the location map where the survey is, it's right up in the Canadian Arctic. Northern Canada is still significantly underexplored, and most of our surveys are conducted up there. So that was a magnetic and radiometric survey. The line spacing can be anywhere from 50 meters, I guess, to 5 kilometers, but it was 400 meters in that case at 125 meters survey altitude. And this is kind of our standard, I guess, for those high-resolution regional framework mapping survey. The nominal ground speed was 75 meters per second, and we expressed size of the survey really in a production metric, which is the line kilometer, so 83,000 line kilometer for the survey, which is a fairly large survey actually. JDS, the company there, mobilized 2 aircraft on site for the survey, and personnel and equipment as well for their headquarters in Montreal to Igloolik in Nunavut, which was the community closest to the survey area. From there, the ferry to the midpoint, sorry, of the survey area was about 150 kilometers, and the survey operation lasted from August to March 29, 2018, with a break because of the Arctic night around December, January. The survey was completed in a total of 107 survey flights and a total flight time of 404 hours. To describe the daily routine the daily operations or routine operations, I'm taking survey flight 29. It was flown on 13 September 2017. The daily operations involve first a series of ground check and validation of the equipment that's working properly. Then the aircraft take off. The AC and escape ferry to the first line in about 30 minutes, and you can see highlighted location of these lines on the survey area. 10 survey lines were completed in about 4.3 hours. The aircraft ferried back to base, and after landing, there was some post-flight checks, data recovery, and flight data QC was done back in the field office of the crew in Igloolik. Airborne geophysics is a very mature field. It's seen 60 to 70 years of development, and the GSC was there right at the beginning. Some colleagues I worked with actually were part of this. Some of this practical knowledge has been compiled in guidelines document, and the success, I guess, of airborne geophysics is in part for sure due to these guidelines. It ensured validity, quality, and usability of the data, consistency between surveys, different surveys and different platform used, different area. It streamlined definitely the work between service providers and clients. At the GSC, these guidelines are very important for us because they kind of ensure the perenniality of the data. This is an important aspect for us because we're investing public fund, and we have to make sure that the data is useful for the longest period of time. As we have just seen, regional airborne geophysics implies significant mobilization of equipment and personnel, extensive logistical and operational efforts, and considering the type of flight operation, so repetitive, prolonged, and requiring accurate navigation, RPAS could provide a valuable alternative to traditional aircraft. There are benefits. There are potential benefits of using RPAS for airborne geophysics. We kind of expect operational efficiency compared to aircraft with a pilot on board, and this would be compounded in increased daily or per flight production, and with reduced deployment efforts being necessary. Accurate navigation that doesn't depend on the pilot skills or is affected by pilot fatigue. Reduced environmental footprint. So because of lower fuel consumption, there will be a reduction in emission of greenhouse gases. And there's also a reduced noise level and disturbance to wildlife, because this is often a concern of the northern communities when we propose a survey. It could allow frontier surveying, which is there are many areas in northern Canada where that are very far from any airport. So the extended endurance of long-range RPAS could provide a mean to reach and survey these areas. Flight operation of RPAS for regional airborne geophysics would imply low-level flying beyond the visual line of sight, and a range of hundreds of kilometers, potentially between the air vehicle and the operator. So to achieve this, a series of challenges not unique to geophysical operations have to be resolved. There has to be BV loss regulation in place. This also means that a reliable radio or satellite command and control link is available. Detect and avoid technology have to be standardized and approved by civilian authorities, so that can be used on those surveys. With the low-level flying, some automation is required, so the vehicle can react on its own to obstacle in case of break or latency in the C2 link or the video feed that the operators see at their end. And there's also I'll point about the logistic and crew management. Like with aircraft, I have the Scan Eagle there that potentially can fly 15-20 hours. You have to set up some sort of crew rotation. With such long endurance, it could fly into the night. So this imply a sort of a new approach to human resources management or pilots management. Consideration for data quality is an essential aspect. Of course, there's no point in collecting data that doesn't fulfill its purpose. So system integration is a critical step. One challenge of system integration, obviously, is the magnetic noise created by the system itself. This is a complex problem, and there's been a few talks this week that have been considering this problem. I'm not going to go too much in details here because you're all aware that this exists, but really kind of standardized, I guess, mitigation approaches in aircraft design, in system integration, and in post-acquisition data processing have to be developed so that problem is resolved the same way for different type of aircraft in different situations. Another challenge is the efficiency. The efficiency of gamma ray detectors depend on their density and volume. So the bigger, the better. And obviously, this poses another challenge for integration within the RPAS, since the payload capacity is most often a restrictive specification of those systems. In this case, we've seen some work on that side from Medusa this morning, but I think more of this is needed, and modeling and trials are necessary to find the best compromise between detector volume and mass and the vertical performance and the flight parameters that will deliver useful data. Oh, I meant to remove that slide, but it's still there. So yeah, I think working with RPAS in geophysics, we can definitely identify two different streams of work or application. There's a new capability that's being developed. It's those localized surveys that cover a few kilometers across, and they're seen, I guess, as an augmentation to ground measurements, while what I've been talking so far is more an existing capability that could be replaced with RPAS and on those regional surveys.
Sorry to interrupt, but we'll want to start to wrap up.
Yes, sure. Here I reproduce the performance of specification for a well-known RPAS system. There's 3 that are sub 25 for magnetic only, that could be used for magnetic only, and the last 2 are heavier aircraft, most suitable for geometric. The main observation, I guess, is the design and performance are very similar. Cruising speed is slow compared to traditional aircraft. And if I consider the Scan Eagle, it's a robust and proven platform. I've seen almost 20 years of operation, and let's see how it would perform on the Gifford River Survey Flight 29 that was presented earlier. With the reported cruise speed applied to it, we see that for the ferry that would take half an hour with the King Air aircraft that was used, It takes about 1 hour with the aircraft here, the UAV, the drone, and the whole flight, like ferry, 10 survey line and ferry back, that is completed in 5 hours or 15 minutes with the King Air, takes close to 13 hours with the Scan Eagle. So moreover, if we were to extend the flight to the endurance of the Scan Eagle, it could achieve to fly 14 survey lines in 17 hours and 23 minutes. So we have to keep in mind that the spatial resolution would be 2 to 3 times better, but the impact on flight crew management have to be considered, because the aircraft has to be staffed all the time, obviously. There's probably some aspect of the concept of operation that could be updated. So pilots could be located at a remote location and the headquarters of the company with a better set up flight deck, so it's more comfortable to rotate pilots. And as well, a reduced then field crew could be sent on site for maintenance, recovery of the vehicle and data management on site. The company, the operator of this King Air, reported the fuel consumption, which is 270 liters per hour. So if we extend that to the fuel flight of 5 hours, so we get 1,400 liters that were used, and with the current cost of jet fuel, it gives a total of around $860. I can't find really a official quote for the fuel consumption of the Scan Eagle, but I can figure out there's about 5 kilograms of cargo available for fuel, so 4.35 liters. So that's a full flight. So that's about $3 of fuel for a whole flight.
Sorry to interrupt. We're going to. This is great, but we're going to need to wrap up so we can move on to our next speaker. Thanks.
Okay, sorry. Using my conclusion here, live trial, I guess, are possible at smaller scale, and you see the other conclusion on the screen. Thanks very much. Sorry for being so slow.
No, I think folks are super interested. So, but we'll have time to circle around. If folks have questions, you can put them in the Q&A box, and we'll circle back to those in our general discussion. So that was really interesting. If you could stop sharing, then yes, Geoff can start. So that was great. Exciting to see so many of the different aspects of what are going on with heavier aircraft, fixed wing, and rotors. So our next speaker will be Geoff Pettifer, who's talking about guidelines for drone geophysics. So we can see your screen. If you want to go into presentation mode. Great, thank you.
And you can see the laser pointer?
Yes, all looks okay. Good.
All right, thank you. My name is Geoff Pettifer, and I'm presenting on behalf of the Near Surface Geophysics Inter-Society Committee on UAV Geophysics Guidelines and Standards, a wonderful group of people. I'm with a company called GHD. I'm also an earth enthusiast, and I have my own private company called Terra Antheos Geoscience. So I hope this presentation is of interest to you, and thank you for your attention. It's not advancing for some reason.
You need to click in the screen and then use an arrow.
Yeah, I'm using an arrow. Oh, there we go. Okay, so the roadmap of my talk. First, I'll introduce the committee, talk about the motivation and why we need guidelines. We'll talk about the philosophy and structure of the guidelines committee and approach to what we're doing. We're mostly concentrating initially on magnetics guideline as a template, and then I'll move on to briefly what's happening with other sensors. And finally, a lot of good information here, particularly an advance in capability and knowledge since the last summit. We'd like to share with you how you can contribute. So who are we? Well, the committee is basically a group of people that belong to the societies that you can see on screen, and not only some of the major near-surface geophysics societies, but also things like the IAH, the AEG, Petroleum Exploration Society of Great Britain, and we have a representative who is a member of IAGSA. Now, these people are volunteering their time. They don't officially represent these societies, but in that sense, we're inter-society. We're trying to operate outside the bureaucracy, but keep the societies up to date. This is the committee, and you might recognise a number of these names. Quite a few have presented on this talk. I won't go through them in detail. We'll come back to the committee names at the end of the talk. But please get in touch with any one of these people if you want to contribute. And I'd like to pay tribute to the companies and the organisations that these people are working with, because they're giving up their own time and they're giving their intellectual property to share with the broader community. And this is just the broad range of consultants and engineering companies, service providers and universities that are on the committee. And please, we'd be very happy if some of you with great experience would add your name and your company brand to this committee. So why have guidelines? First of all, as we saw with James Jensen's talk, and from anecdotal evidence, about half of the drone surveys in magnetics in Australia are below standard because a lot of people are not geoscience trained. And so all these operators, whether they come from a geoscience background or they're lay personnel, need to understand the basics of good drone geophysics acquisition, noise mitigation, data reduction and processing. And everybody's on a very steep learning curve. And the drone geophysics comes from different challenges compared to using ground geophysics or airborne geophysics. And if we have bad data, it's going to eventually give our industry and profession a bad name, and none of us want that. And we particularly don't want to have bad safety incidents by people that may not be fully responsible in terms of their operations. And we certainly don't want that, because it may end up in restrictions on responsible operators. Now, if we have guidelines, it's going to protect clients, it's going to protect people that write specifications for surveys, that QA, bird dog the surveys. It's going to help everybody. And we need experienced operators like the people that have presented on this forum, to share their wisdom and knowledge of good practice to help bring all operators up to speed quicker, because if the industry is performing well, then it's a benefit for us. So why guidelines are not standards? We had a bit of a debate about this and decided to stick with guidelines because standards are very expensive, time consuming to develop and update. Societies can almost go broke trying to develop them. Difficult to get agreement on, hard to mandate and enforce. But the guidelines provide interim order to the industry, and with voluntary adoption, there are plenty of benefits that I'm sure that all of us can understand. So there's continuous improvement of practice. So we want something which is readily updatable, and guidelines are a more nimble way of doing it when you look at the process involved in updating standards. We're looking at also providing optional approaches, because new methods of data correction develop, and there's several options often available. Now, if these guidelines are adopted and stabilised over time, they can provide a technology transfer pathway that may lead to the development of standards, but that's down the track. If we look at the philosophy and structure of the Guidelines Committee, well, primarily, as I said, we're looking at providing a primer for clients and for geophysicists, geologists, operators, on good practice with a relevant sensor. And at the moment we're focusing initially on magnetics. Our philosophy is don't invent the wheel. As we've seen, there's a lot of rapidly growing knowledge comparing the summit from last time to this time. So we embrace the ready-made, reference the available and rapidly proliferating literature, particularly reference standards and guidelines that are already in place. So the ASPRS, for example, has published standards on the LiDAR and photogrammetry. Particularly, we're mindful of drone safety standards and we promulgate these in the guidelines. We don't endorse any product over another, but we've had some debate about the merit of providing comparative tables of drone equipment, software performance and key capabilities. Now, it would probably be for us to define the parameters we're interested in and for the providers to populate them. It'd be interesting in the discussion to see whether people think that's a good idea or not. We've got to emphasise we're all volunteers, we're all busy people, and the key challenge is meeting often enough and developing these guidelines fast enough when there's so much change occurring on this steep learning curve at the moment. So we definitely welcome voluntary input to the committee and subcommittees and for our knowledge sharing debates and guideline development process. And we try to provide progress reports to the various NSG societies. Hopefully they'll be able to review the document and provide some sort of tacit endorsement. Now, I said that there are standards available and literature. An example here on the left is the ASPRS digital geospatial standards, which have been around since 2014. Richard's talked about the standards for here for the airborne geophysics, and Australia has some as well. Recently, a document came out, which I think Jan Frank was part of the co-author of that, on developing UAV-mounted geophysical sensors. And there's a public document, and you can pay for a more detailed document with Amira Global. Really good publications are now coming out on very, very detailed review articles, which do a lot of the work for us in the guidelines. Unmanned aerial vehicles for magnetic surveys, a review of platform selection, interference, suppression. There's one on coverage, survey coverage path planning and reviewing what's available in that. And there's several available on review of applications. Everybody that just about has worked on plant stress is referenced in this, for example, this reference. I should say that I can provide a PDF copy of this this talk to whoever wants it. Don't worry if I brush over things quickly. Now, looking at the structure of the committee, we have subcommittees on magnetics, radiometrics, electromagnetics. Gravity is a subcommittee of one. We're just keeping tabs on that at the moment. Unfortunately, we don't have anybody on ground penetrating radar, so we're looking for volunteers on that. And you can see each committee is working on the specific aspects of the sensor that is under their ambit. We have a subcommittee on survey planning, execution, on positioning, on drone mapping, on safety, and drone platforms. And of course, how active these subcommittees are depends on the busy people that we're involved in. So the more people we have, the more chances that we can keep these things moving. Now, just touch on the magnetics guidelines and some progress on that. We've got a draft structure of the document, and it's probably about 75–80% complete. This is the structure of the chapters, an introduction on the basics, the aims and objectives, the driving factors of technology selection, and the categories of surveys. I'll talk a little bit more about that shortly. The pros and cons of the UAVs versus existing platforms, airborne or ground, vehicle-borne. The available sensors, their noise sources, and the signal noise required for particular applications. The navigation equipment, the XYZ technologies, and the navigation aspects and the obstacle avoidance, the drone platforms, how these are mounted, the firmware and the flight control systems, the survey planning pre-ops, specifications and also the mapping that has to be done to actually properly make sure that you can survey safely in the area. Then there's the execution and operations, the data acquisition, QA/QC. Finally, processing interpretation, post-ops, QA/QC, processing interpretations, modeling software, modeling and version of software. Safety is a big aspect. A bunch of references and if necessary, appendices. So that's the structure of the document. We're hoping with about two or three more meetings that we can have a first public draft released in January sometime, probably towards the end of January, for public review. And we welcome input, and it would be great to get a few more members on the committee just to help us towards that final goal. Now, just a couple of teasers from what we're doing. We're trying to show examples of noise, and this is an example provided by Paul Mutton from Touchstone Geophysics of the maneuver noise of a bird flapping in the breeze beneath a drone. It's an east-west flight line, and you can see quite clearly the sensor motion. So we're providing these practical examples of different types of noise you might expect for the sensor you might be using. This is filtered data on the bottom, taking out the long wavelengths. We're sort of haven't finally arrived at this, but we're thinking about sort of 3 levels of magnetic survey, depending on the application. If you're looking for oil wells with hundreds of nanotesla anomalies in some cases, you may just need to do some simple diurnal corrections and a background removal of some sort. And that's a sort of a level 1 survey. If you're doing geological or geotechnical mapping, you may want to do all these corrections from diurnal down to the heading correction. And if you're doing a level 3 survey for UX and archaeology, you may want to do the full gamut of corrections and even right down to micro leveling. So it's this is a sort of an estimate of the magnitude. This is the nanotesla scale, logarithmic, and the magnitude of the sort of corrections you might have to do in diurnal, IGRF, compensation, heading, and micro leveling and so forth. So this is an example of a workflow in there and different phases of correction. The raw magnetic data, number A. In B is after we've compensated for the vehicle. C is after diurnal correction and IGRF removal, and the final Rolls-Royce is the micro leveling product, which of course we're hoping that everybody will try and do level 3 surveys. Looking at other sensors, there's some exciting developments. On the top left, we see the MEMS system that has been developed at the University of Glasgow, and we've heard from Storm about the developments here at Berkeley. So there's gravity sensors coming on board. This is the work of the Dutch, the Steven van Veeke and Han Limburg and others. This is taken from one of their papers. There's a VLF system, the EM system, which is a passive EM system. There's also radiomagnetic telluric type systems, which use local radio frequencies, developed in Europe. There's the Flying Gem, which is taken from Drone Geoscience graphic. This is UGCS EM61 Lite, and of course we've got Johannes Stoll's MGTs. Roving, all these are frequency domain systems at the moment. But so all of those are being looked at by subcommittees. So the subcommittees are working away as the time permits to just put together the information that's going to be needed for their guidelines, which will be the next ones off the production line. We're going to use the magnetic guideline document as a template. The EM system subcommittee is looking at the frequency domain systems, transmitter and receiver on the drone, such as GEM2 and EM61 Lite, and the transmitter on the ground, such as the MGT system. And of course, I've mentioned the passive.
Sorry to interrupt, but if you can start to wrap up, that'd be great.
Yeah, EM signals. This is my second last slide. The passive EM signals, the drone radiometrics systems, the Medusa that Stephen and the Canadians and US are developing. We definitely need somebody from the GPR side. Drone gravity, watch this space, and maybe we'll look down the track at thermal and hyperspectral imaging, although there may be sufficient guidelines around for those. So how can you contribute? Join the committee, subcommittee, review the draft guidelines, send your ideas to any of the committee. We particularly like some good examples of noise, processing workflows, process data and case studies, and advice on good references to reference in our guidelines. And these are the contact people, Ron Bell or myself. I'll just show that in the next slide. Thank you for your attention, and we'd welcome some discussion about how we can advance these guidelines quicker and more regularly. So thank you, everybody. And particularly thanks to the committee. Please get in touch with any one of these members of the committee.
Thanks so much, Geoff. That was great. So I think we're going to move on to our full discussion section. So this has been, I just have to say, this whole week has been incredibly exciting to me to listen to everyone's updates on advancements in developing new sensors, optimizing data collection with existing systems, and expanding our capabilities in terms of multi-aircraft setup, including automated swarms. So it's amazing to see year to year the changes and how quickly things are changing. So we have some time right now for general discussion to follow up on our morning speakers, and then, well, morning here, I'm in California. And we'll also have a larger discussion about sort of future directions for this event and larger community needs. So for right now, are there any discussions or questions that folks have based on this morning's speakers? Any additional questions? It looks like a few folks have stepped out, so I think Tom and Storm are no longer in the discussion. But for other speakers, any questions? And I think Lori's going to be switching us over to participant mode, everyone to a panelist mode for the discussion. So you'll pop out and in as that happens. So we have one question from Seppo. Does anyone know of any experimental surveys actually accomplished with whatever type of gravity sensor attached to a moving UAV platform? Are any of our speakers? Well, I'll have to table that one if not. Other questions? So in terms of general questions, I'm really curious to hear sort of, after listening to all the speakers this week, I'm curious what folks think are the overarching challenges or needs that we have as a community, as a geophysics drone community, and that we can actually work together to solve as a community, to come together. And so I think Geoff's examples of looking for guidelines and standards, and developing that is one aspect. So I'm curious what folks think are priorities. And as Lori moves us all into panelist mode, you'll be able to unmute yourself and just speak. So that's an open question for any of the panelists from this morning, or any of the organizers, or any participants at all.
Well, maybe I can I can add something. I think the last two talks were actually very interesting in the sense that I think they actually touch on the maybe on some of the problems that we are still facing, and that also holds for the talk of on the say the legislation part of the of working with drones. I think it is indeed very important that we get to a certain form of say best practices or rules and also to be able to translate that into a form which is easily accessible for people outside of our own domain. Because I think what we notice is there is a lot of people working with drones, and there's a lot of people that are actually looking around for applications, and which is also a problem that many people are well, just going out and trying to do things. And I think it's important as a community that we basically set the record, or at least create the kind of a standard in the way that we should do this kind of work. At the same time, it's also, if you compare what is happening with say the drone kind of applications, it looks pretty far away from, for instance, the Canadian GeoSurvey standards that were discussed by Richard just a moment ago. And so yeah, it also feels that we are still at the brink or at the start of a kind of, you could say, a step towards professionalizing using the platform for geophysical application. So I think there's still a lot of work to do, but I think it's very important that we actually follow up on the efforts that were just described by Geoff, and make sure that we have this this standard work, so to say.
Thanks, Han. Other thoughts?
I've been curious about standards. I did some work with AGSA a few years ago, and I'm curious what's, from the panelist perspective, there's advantages to the industry, certainly, but from a competitive commercial perspective, is it the standards also saturate the industry with more competitors, oftentimes because all these standards are born from very blood, sweat, and tears, I suppose, and from experience of broken drones and bad surveys, etc. And so, yeah, I guess what's the experience of those on the panel with standards, and has it been a good experience from a commercial perspective?
You mean in terms of using standards, or how? I don't really see the link between the commercial perspective and the standards.
Yeah, just being involved in creating standards for operators, I suppose, because I mean in this case the enemy, if you want to use that word, are bad operators. They mar the industry and encourage heavier regulations from a government perspective, which are onerous and difficult. But yeah, and I suppose collaboration between respectful competitors is usually appreciated and often helpful. But just wondering what your guys' experience has been.
Well, I think, I mean, if you look at standards, there's always, I mean, a kind of a generic discussion whether this is actually withholding, for instance, innovation or not. And I think, as this kind of application is still, there's still a lot of innovation going on. So I think in that sense, best practices is maybe a better term to describe the need for the industry at the moment than standards. We still have to find out a lot of things and maybe also develop a lot of things. And especially if we've seen some of the talks this morning, for instance, on the gravity and everything, I mean, there's no way that you can actually talk about a standard there, I think. But I think a way of starting with best practice, how should you do a survey like this? What are typical boundary conditions in using a drone? What kind of line spacing are we talking about? Well, there's lots of things to mention, but I think at least a kind of bare bones document will help everybody. At least in explaining. Our experience is that it works Well, basically, we are answering similar questions all of the time at the moment. If we get inquiries by people that have drones or that want to use drones, and they say you have an instrument that we can put on it, they'll be asking the same questions over and over again. And it will really help if we can basically tell them, okay, go look up, there is a document, or there is a working order or something, and which is not Medusa in this case, but which is actually accepted by the community. And I think that is going to help.
Yeah,
so we've got a few hands up. So I just want to acknowledge those. So Gary Young, do you want to go?
Sure. I have experience doing guidelines and standards in the civil engineering application area of geophysics, and I can tell you that the discussion that we just had is right on. The problem is that the smart people, the ones that know about the problem, are the ones who tend to establish these things. But then if you have a guideline and not a standard, then anybody who can get the copy of the guideline and say, oh, I'm doing this, and you will spawn a lot of people that don't know what they're doing. And the problem is, just exactly as has been stated here, getting a standard put in place is really hard. And so you're in for some years of bumpy going, in my opinion, because the standard I'm thinking of in the civil engineering area was established in 2002, and we're doing the second version of it this year. And in the intervening years, we had lots and lots of troubles with people getting in the business that didn't really know what they were doing. That's about to settle out now, but it has taken a long time. I hope it doesn't take that long a time here, but I think we are in for some bad times, and we should be ready for that. And I don't know exactly what you do, but making sure that the public out there that buy this services know who the good operators are is really important. Thanks.
Yeah, if I could just come in
so
here.
Jeff, I actually want to go on to some folks have had their hands raised for a while.
Sure, okay.
So I'm going to go on to Morgan, Jeff Gamey, Jan, and then Jeff, we'll circle back to you.
Thank you, Kian. I just wanted to add that, so I work for a company, Guideline Geo, we're the manufacturers of Malo GPR, and some of you probably know that we have a drone GPR system as well. And what I have observed over the last couple of years through the development of that system is that there's still a lack of knowledge of certain things related to impacts of the actual drones themselves on our different sensors and the data that we're collecting and things like that. And so I'm personally a little concerned about creating standards for how things are done with kind of the lack of information that we have. I've worked for multiple companies now that have been developing systems that work with autonomous vehicles of different types. And some of them are really good at trying to characterize the impact of those autonomous vehicles on the sensors, and some are not. And if we learned anything from, I think it was Tiffany's presentation on the first day, like we still have a lot of questions about the impacts of these different survey types, right? So while standards are really valuable and guidelines are certainly a good thing, I would be worried that we are not ready to create all of them. Obviously magnetics is kind of an exception to that because it's been practiced for so much longer than everything else. But yeah, that's kind of my 2 cents. I'm a little worried that we might be jumping the gun.
Thanks, Morgan. So Jeff Gamey, you had your hand up.
Yes, I work for Tetra Tech, and we're mostly involved in the UXO geophysics. And I can tell you that that industry has adopted a standard, the ISO 17025, as a standard for what they call advanced geophysical classification. And those requirements are extremely onerous. And the emphasis on quality control is almost as expensive as the actual operations, in order to comply with the standard. And it has brought about since all of the industry is working to that same standard, all of the providers are producing essentially a commodity product, and the cost or the only deciding factor in choosing it seems to be the final cost of the thing. Now that may be just that one specific industry, but that was my experience with standards. So I would think that in this case for drones and the rest of the geophysical community, I think standards like the ones we have for magnetics and radiometrics in exploration industry generally are probably a much better way to go.
Thanks so much. Jan, you had your hand up. Want to jump in?
So I'm actually going to disagree with Morgan a little bit. And I've been involved with standards or attempting to implement standards in the GPR community for 25 years and being tremendously unsuccessful at it. Primarily because GPR is one of the most over-promoted and oversold technologies, and it's considered a black box technology. And I'm going to speak specifically about GPR. Right now, I'm in Canada, and we have an issue with our First Nations, as many of you might be aware, where GPR is seeing a lot of public interest. And speaking of standards, we're trying to implement standards across Canada for First Nations residential school surveys, and it's not going well at all because every operator wants to do it on the cheap and make as much money as possible and are claiming absolutely ludicrous results, ones that our Prime Minister have responded to. I mean, it's gone to that level, and it's embarrassing for us in the industry. From an Australian perspective, Geoff, I'm shocked that you don't have somebody on the GPR side. I'm happy to help, of course. But there's an operator, a well-known operator in New South Wales that is attempting to put a megawatt radar on a drone. Now, the implication of this is you've essentially got a electromagnetic pulse bomb, which can kill somebody with a pacemaker. So this is not just about standards. This is about the survival of the GPR industry and perhaps drone geophysics in general. One major incident at a mine site, for example, in Australia, will paint us all in a very black way. So I think standards are needed. Whether we're still learning about this interference from RFI from the drone itself is kind of inconsequential. But there are laws that we must keep the drone within 1 meter of the ground when using GPR in this case. The actual operational types isn't really relevant to the standards. It's what we can do and what we can claim with drone geophysics, I think, is super important, as this is this nascent technology.
Thanks, Jan. Geoff, Pettifer?
Does Cullen want to speak first, or?
No, you can go ahead, and I'll follow up after with a couple thoughts.
Yeah, look, I think all these comments are valid, but I think what we have to avoid is what I could term standards or particularly guidelines paralysis. Because it's hard to do these things, we shouldn't shy away from it. I think what we're, as I tried to point out in my philosophy segment, that basically it's better to have some document there which is evolving that provides, this is what we know and this is how you go about doing things properly. This is what we don't know. And I think that'll get around the problem that you raised, Morgan. If we don't know certain things about GPR, then let's say so, and then maybe the next version of the guidelines for GPR will actually solve that problem. And I agree with the comments of Jan that yeah, one seriously bad incident, particularly at mine sites, is going to really impact us badly. So I think we can't afford not to do guidelines. Yes, standards are tremendously difficult to develop. They take a long time to update, and they're almost out of date as soon as they're published. At least with guidelines, if we have plenty of voluntary input and IP input from people, then we can hopefully keep them up to date fairly regularly. And everybody can say, okay, look, this survey was done to a level 1 standard or a level 2 or a level 3 standard. Everybody understands, and hopefully eventually these bad operators will be weeded out unless they understand the basics of the guidelines. So I think let's not get paralysed about about the difficulty of getting standards are extremely difficult, but guidelines are maybe a lot easier.
Thanks, Geoff. So next is Mel, and then after Mel will be Callum.
Hey, thank you. So I really appreciate the efforts of the committee, Geoff and others, in trying to establish some type of guidelines. I am wary of some people who are really pushing towards this idea of standards, because like many others have said, this is such a nascent field in many cases, and we still don't know what the actual standards should be. And like, you know, to reiterate the point that's been made already, that once standards are established, they're already out of date. But coming at it from another perspective, from the academic world, which is University of South Florida, we are always coming at these things, always a step behind in terms of funding and in terms of money for what we can do. So we are in some sense sort of the little guys when it comes to geophysics. So if you establish a rigid set of standards, a rigid set of guidelines, you are going to cut out, and you're essentially gatekeeping a community who are potentially coming up with some of the innovative stuff that industry can then take on and develop for profit. So it is a little bit of a risk if you end up going down the you must do it this way, that you kind of cut out some of the more innovative, small scale projects that are going on in a time when this field is still developing at such a rapid pace.
I think that's a good point. I mean, I think we can have, as Han pointed out, we can have some basic parameters about the things that you must do, and people, I'm encouraging people that are doing innovative things to share the outputs and the product of what they're doing without giving away the internal workings of it. You know, if there is a particular better ground, you know, a ground clearance control system, then we can reference it, and people can know that it's available, and they can make up their own mind whether they want to go with that innovation or stick with the current innovation and so forth. So I don't think we can stifle innovation. I think we can still protect IP, but just point people to what their options are.
Thanks, Mel and Geoff. Callum, you're up next.
Awesome. Yeah, I just had a couple points kind of building off everything we talked about, sort of innovations, applications, and then one of the main things I wanted to bring up was kind of professions. And myself, I'm a member in Canada of 2 professions, and we have to adhere by certain standards and guidelines, whether it's the airborne geophysics industry, whether it's an engineering profession. And the problem I see, and I think why we bring all this up, is just kind of the cowboys that are out there picking up geophysics instruments, attaching them to the drones, thinking they're cameras like photogrammetry or something like that, and saying they can do geophysics surveys. When, you know, you ask them, have you used a base station? Have you done any of this leveling and stuff? They just kind of look at you like with a blank stare, because they have no idea what this stuff is. So I think the standards and guidelines are just kind of almost a bare minimum to, again, this idea of weeding it out, or at least setting a standard of, you know, these people actually are somewhat trained geophysicists, part of this profession, that can do these surveys in a way that, you know, adheres to some of these different applications. In terms of applications, again, there's some that are, you know, might not need as high of guidelines or standards, and then there's some that definitely do, such as UXO or something like that. I think the main idea with this is just to kind of get an education on the commercial side for people to understand what's going on. Because right now you might have a junior mining company that, you know, goes out and looks for a survey. Someone undercuts the geophysicists that are doing this properly by, you know, $50 per line kilometer or something like that. And then companies are turned off by it because they get data that is just, you know, garbage, nothing that they can do with it compared to maybe something they're used to elsewhere. In terms of innovations in the academic world, I think, you know, that's a valid concern, but I don't think what we're trying to do is stifle innovation here. I think the people who are doing a lot of the innovation on the front side of this are kind of above and beyond the guidelines and kind of standards that we're looking at. We're not trying to, I think, stifle innovation. I think the people that, you know, would go through with this would, kind of shine past a lot of what these guidelines and things are and kind of help gauge this. So those are just kind of some of my thoughts on this, because the thing that I see in the issue with this more often than not is just people that haven't had the background and training to understand kind of what they're doing with these sensors and what kind of data processing has been established for well over 50 years in a lot of cases. So.
So I want to also notice, so this is a great conversation. I also want to acknowledge that there's some questions in the Q&A. So let's see. Thomas, I think, spoke earlier, but also said, I suspect that UAVs will offer alternative operating methods. The Scan Eagle, as an example, would work really well for 24-hour operations. Jeff asked the question, does anyone have a read on the current status of Chinese drone ban on US federal projects? Is there anyone else who wants to answer that, or I can?
This is Nathan. I've been out most of the day, but yeah, I can speak to that a little bit. They are sticking to that as of right now, but you know, it's kind of a gray area where you can apply for a waiver to get it to not use it for like a short amount of time. And that just depends on probably which branch, which agency. If it's DOD, I'm thinking it would probably be really pretty strict, but other governmental agencies have more leeway with that, from my experience.
Yeah, I can speak to it a little bit too. So there's no single, right now, there's no single overarching sort of standard across the different departments in the US federal government. So it is, as Nathan was saying, really on a case-by-case scenario. There was an executive order from the Trump White House that came out in January, and the current White House will be following up on that in the near future that affects drone operations. And there's pending legislation as well that could have implications. The other piece is that some folks may be aware of that there's a Defense Innovation Unit Blue Drone program. I think it's called the Blue SUAS, and that's DoD approved sort of commercially available drones that meet certain specifications. And there's going to be additional adoption of that probably across a lot of federal agencies. So we just look for the Defense Innovation Unit Blue drones. But it's a rapidly evolving, but also slowly evolving situation. So am I missing any hands? Other thoughts or questions? We have a couple more minutes, and then I want to turn to the question of sort of planning for our future events. Any burning questions, thoughts, comments before we do that? Jeff, go for it. You're muted.
Yeah, a question for Han. I've got a question on the relative sizes of the upward-looking crystal versus the downward-looking crystal. I know in aircraft, the upward-looking crystal can be quite small.
Mm-hmm. Well, basically, this is something we are designing at the moment, and the idea is actually to fully cut a crystal, circular crystal, cylindrical, in two halves, and have a reflective layer in between the two halves. So basically, any event that will get or will be created in one of the halves will not get into the other one. And it's kind of a sandwich construction. And this is done, has been done before in Compton shielding kind of things. And but basically, so what it boils down to is that the upper half of the crystal will be completely dedicated for looking at the radon from the sky, and the lower half to the signal from the soil. So it's a 50-50 division.
Just a follow-up question. I know that radon seems to be quite predominant in the valleys in the morning. and then the sun disperses as the day warms up. Have you found that to be the case, or you're just working on very flat terrain in Holland there?
Well, yeah, in Holland it's not really a problem, but no, I think that is what you see, and it depends. I mean, what we've seen also in it is that it's basically if you have inversion layers, for instance, in the air, then of course the radon will also more or less stick to the lower parts of the of your of the layer of air. And I think what we've seen up to now is that indeed in valleys or in those kind of areas, the problems are likely to be larger. And of course, after rainfall, I mean, then you will have a large amount of say the decay products of radon falling basically getting to the topsoil, and that's also going to disturb the signal quite significantly, which is something you can solve by just waiting for a couple of hours before you go out again.
Thanks, Geoff and Han. Ron, you had your hand up, and then Richard.
Yeah, I'm sorry, I had to unmute. I just want to make a few sort of observations. Standards are sometimes, as people have noted, they tend to diminish interest in applying things, and but they tend to, partly because I think because they tend to commoditize, and at some point geophysics, as we've seen with GPR and other technologies, geophysics is heading towards a commoditization at times, and for certain markets and certain applications. The reason that that the guidelines thing came about is because the need to actually help people who are not maybe that familiar with either drones or geophysics in general is to help at least guide them in doing it the right way. And then from that point of view, I think we will all benefit, because it's not a complete effective strategy to diminish bad work, but at least it's a movement in the right direction. Now, one of the things that I try to I've been up against a little bit is that I do work. I find project areas that I can go and test systems on, and then they dig the doggone things out of the ground. And because of a lot of its development areas, there's residential development, and a lot of the things I want to test, they don't particularly want to have it in the ground. So one of the things that I'm trying to propose, at least for my work in Colorado, and I think it's probably useful for everybody, is if we had a set of sort of test sites that people could go and do various things on the test sites to test their instruments and test their effectiveness with drones and training, and overall, I see these as beneficial. I got fortunate in that a couple of weeks ago I was visiting. I was actually flying on what was established as a drone park, and I was demonstrating the magnetometer. And what I realized was that the things that we tend to look for tend to be out of sight. And we could, and I'm speaking in terms of the very near surface domain. I'm not talking about things that are, more exploration oriented or geological mapping oriented. But the idea of having places where people can go and test their equipment, as well as do a variety of other things, like I did, demo it, to me is a really positive step in the right direction. So I'm stepping up and saying I'm moving forward with the effort to try to establish this site. It's already established as a drone park, and establish it as a place to to publicly, and anybody can come and test their equipment or demo it and get access to it. Of course, there's probably some constraints on that, but generally, I think that we probably need a series of these all over the globe, so that we're all kind of on the same page in terms of the kinds of things that we're trying to measure in the subsurface, and I would say we all benefit when it's all made public. So anyway, that's my comment.
Thanks so much, Ron. It's exciting to hear about. Richard, next, you're up.
Yeah, so I just wanted to second Thomas' comment on the Q&A about I'll try to use alternative operating methods, switching subject a little bit, but you know, for us on our side, I think porting our technical, you know, doing a simple port of our technical requirements for airborne surveys to drone, you know, would not take advantage of the full potential capabilities of drones. So this is kind of why, in some extent, this armchair project I summarize exists, is because we wanted to see how the overall concept of operation would change, and there's maybe some loss. Apparently, there may be some loss in some areas, but there will be more gains, I guess, in other areas. That's it.
Thanks. With that, why don't we segue a little bit into a slightly different conversation in terms of looking forward and planning for this event in the future. Before I do that, I want to just say a huge thanks to all the presenters from today and from this whole week. It's really been great to hear the latest of what's going on, and it's great to see the variety of presenters, the variety of tools and methods. It's really expanding, and to see new folks coming into this conversation, folks who've been at it for a long time. And I also just want to thank the organizing committee, especially Morgan and Laura, our co-chairs, and Lori, our SEG support. So they're the backbone that made this happen with a lot of blood, sweat, and tears. And I want to, just as we are thinking about next year, I want to give a shout out that Laura will actually be the chair for next year's meeting. So keep an eye out for opportunities to volunteer and support in that organizing. And so with that, I guess my question is, what would you like to see in this event for next year? You know, what worked about this one? What changes would you like to see? Is the virtual event, you know, depending on what's available next year, would you prefer to stick with a virtual event? Would you prefer an in-person event? And this is the second year we've done the full multi-day virtual, but historically there were full day after at the end of SEG events. So the last 2 years we separated it out and did it multiple days on its own. So what would you like? What worked for you this year? What would you like to see next year? Dennis, if you want to go. Oh, sorry.
Go ahead.
Dennis, do you want to go?
Oh, yes. Thanks, Ken. Would it be possible to
right now
show my screen?
The purpose of this event is to serve the drone community, specifically the geoscience or geophysics drone community. So you are the community. We'd really love to hear your feedback. After last year's event, we established a technical committee. So we are happy to have anyone who's interested join the technical committee to continue to drive this event in the way that this community finds most successful. And we'd like to hear your feedback. So please raise your hand and share your thoughts. Yeah.
Of course, I'd like to see an update on the standards, but it's interesting. The first summit was where we defined a lot of problems that we're dealing with. The second summit is where we're actually you know, publicizing how we dealt with those problems. And I think it'd be great to be able to have more case examples on processing data. And, you know, how to overcome some of the problems we find with the processing we're doing. And also then maybe we can even then move into the realm of interpretation and how the drone acquired data is proving to be better than the regionally available magnetics or radiometrics and so forth. So I think start moving more into the processing and the case histories. Yeah.
Excellent. Gary, did you want to say something as well?
Sure, thank you. I would just want to say, having attended both of the summits so far, I'm very impressed with the progress that people have made since the first year. I agree with Jeff. We've done a lot of good stuff, and I look forward to just seeing the progression of that, because there's a lot yet to do, a lot more to go, and I think there are an awful lot of smart people thinking about this stuff now, and I just really look forward to what will come. I don't know that I would want to limit the scope of the summit next time very much, but maybe have a highlight or something in areas that we think are important. But I just want to congratulate all the speakers and everyone that had anything to do with this, because I think we've made great progress. So thank you.
Wonderful. Laura.
Great. Yeah, so I guess on that point, we were wondering, so it's been a geophysics drone summit. Do we want to expand that to other topics in geoscience, such as photogrammetry or LiDAR? Or what are people's thoughts? Are they?
Can I just jump in here? Because we have some poll questions that I was asked to distribute. And so while we're working to get the slide from Dennis, we can go through these poll questions. How's that?
Sounds good. Yeah, I think one of the questions was what I was going to bring up. So perfect.
All right, perfect. And there's no, you didn't even spell summit correctly.
I think, Laura, in terms of the question of the scope, I think that's a challenging one because, but I think there's also another question of, integration of drones into multi-method geophysical surveys, which is sort of a separate category in terms of, it's not everything, but it's integrating drones into specific geophysics work, even though the sensor might not be a traditional geophysics sensor. This is something we debate about a lot in terms of like, does thermal IR, hyperspectral, is that considered geophysics in this context? And I don't have a good answer for that one, but one of the lines we've been drawing is integration, so that it has to have some geophysical component to the larger context, even if the sensor itself is not a traditional method.
Yeah, sure. Yeah, I was just mostly commenting. I'm a pretty much a total drone newbie here. But we recently acquired a couple of drones, like I said, for our field programs. And while we do plan on using them to run some geophysical sensors, we're also thinking of things like just helping optimize our field programs in general, like for doing recon and things. I'm also hoping we can get ourselves a LiDAR unit. I personally do a fair bit of ground-based gravity surveying, and being able to use a LiDAR unit to make our own DEMs is another possible application that could really be a big help. So I guess that was more of a comment than a question. Someone was asking if we wanted to expand the scope next year to include a broader range of topics. Like I personally would have some interest in that, because I'm in my position. I'm a field geophysicist, but I'm open to using these drones in any way that helps us out.
Thanks, Nicholas. Mel, I see your hand up.
Oh, hi there. Just to respond to that about whether to include things like LiDAR and photogrammetry, I would say one of the things I particularly enjoyed about this summit has been the focus on these real pure geophysical techniques, which I do photogrammetry myself. I do multi-spec, I do all kinds of stuff. So I'm all for sticking as many sensors on a drone as we can. But one of the things I've really enjoyed is just this focus on the geophysical sensors, rather than going down the LiDAR and photogrammetry routes, which are much more popular, much more well used, and kind of have their own outlets of people present these things all the time with LiDAR and photogrammetry. So it's not that I'm against LiDAR and photogrammetry, but I just really appreciate the very technical nature of all of these talks in this summit, and the fact that they're really focused on geophysical methods.
Great, thanks for that feedback, Mel. And sorry I dropped out there a little bit. Yeah, good to hear people's feedback on that. I don't know if we got the poll up and running. Did we while I was dropped out?
Can you see it? The result?
Yeah, it looks like we're almost an even split between virtual and hybrid. This is your chance to influence.
Yeah.
Quick vote.
Yeah, so of those that selected hybrid, it looks like about 50% of those would actually be able to attend. So good information. We have, oh, okay. We have another survey, another poll for us. And
yeah, just a philosophical comment, picking up on the last two comments about LiDAR and photogrammetry. I think the photogrammetry and LiDAR standards are well in place, so we don't have to talk about the standards. But to me, photogrammetry is basically geophysics because it's reflectance of the Earth's surface. The simplest geophysical and probably one of the most powerful is the topography, because it's basically the simplest measurement you can measure of the Earth, and that's the elevation. And in terms of case histories, visual images of the surface and topography can be extremely powerful geological interpretation tools. So I think these two summits have been about trying to get our stuff together on how we actually properly acquire these new geophysical techniques. But the LiDAR and photogrammetry are pretty well covered, and maybe even hyperspectral as terms of their standards of acquisition, processing, and so forth.
okay, we have another survey up, another poll, and people have been rapidly answering those, so that's good. And it is to what we have been talking about, the summit focus. Should we expand the focus to include some of the things that people have been talking about, like photogrammetry and LiDAR and stuff like that? Or should we keep the existing focus, which is on geophysics? And it's close, but we do have a leader, and it looks like 52. Oh, we're shifting still. Okay.
Thomas, do you want to mention your suggestion?
Yeah, I agree with the focus on geophysics, especially because it's not seen anywhere else in other conferences. However, using drones in associated ways is developing rapidly. LiDAR especially, lots of benefits to the geophysical application, but it's a whole nother can of worms with all its intricacies. But it would be great to have resources or workshops, vendors, whatever, kind of around the SEG workshop that's focused on geophysics, so that there's at least an outlet for these other topics that many of the people attending probably would be interested in.
Okay, well, I think a lot of people feel very much the same way. Well, not a lot of people, about 55%. I think that this niche focus on geophysics is maybe the way to go. So there you go. Those are the results. Thank you for voting. I have a couple more polls for you. And this next poll has to do with timing.
Outside of operatable drone conditions would be ideal. So yeah, the November is nice that way.
Yes. Well, it looks like the end of October. Let me end the poll. How much people want that? I'm in the field right now, rather outside. The farther outside the field season we can hold this event, the more likely it is that I can attend. Okay, so we have someone who's in the field right now. And I guess I would assume. And also I was reminded that the last 2 years, the summit has conflicted with the Unmanned Canadian Conference.
Laura and Morgan, do you want to take it away?
Yes, sorry about that. I couldn't find my screen. Well, we just wanted to kind of wrap up. I know, Dennis, you had one thing you wanted to mention briefly. Have we sorted that out?
I'll just talk to this if I can't show my slide. I'm not sure if Callum got it or not, but
And do you have did you get the email?
I'll just speak to this. The BC, I'm representing the BC, the British Columbia Geophysical Society, and we've decided to have a workshop on drone geophysics. This is going to be an in-person 2-day workshop in May of 2022, next May, in Vancouver. The first day, and by the way, we planned this actually for November of 20, and had to cancel because you couldn't do an in-person workshop then. And so we put it off until May of 22. The first day will be classroom presentations at a downtown university campus. The second day will be live outdoor demonstrations at Burnaby Lake Park. And that's not far, that's basically right in the city. The slide that I wanted to show you was the air restriction map of Vancouver, and it's in a spot. It's actually at a location where hobbyists, remote control plane hobbyists, fly their planes. So we're using a spot that already has approval. So we'll have demonstrations at this park, basically right in the city. This conference is going to, this workshop is going to focus on drone technology rather than geophysical data itself. There'll be geophysical data shown, but it's really the presenters will be mainly discussing the technical aspects of their drone systems used for geophysical surveys. And we're going to focus on both presently used systems and techniques, of course, but also where drone technology and applications are headed in the future. So I'm hoping to look ahead a lot with some innovative ideas. And this will cover legal aspects as well as the engineering developments. So I know this is all meant basically for North American and Western North American audience, but this will be a 2-day in-person workshop in Vancouver in May. In the new year, January, we'll be sending out some announcements and lining up the presenters and the people who are demonstrating. Great. Thanks for the opportunity to show that.
Wonderful. Thank you, Geoff. I think if you'd like to put your email in the chat, so anyone who's interested in contacting you for more, they can do it that way. And aside from that, I wanted to say a thank you to everyone who's participated with us and joined us for this event, both this year and last year. As you may have noticed, we've had many repeat, both participants and some presenters, although one of our goals this year was to really try and make sure we had a larger presenter body. As we all know, we can sometimes hear the same people's voices over and over again. So we love hearing from new people and seeing what's happening in other areas. So for next year, please share with those in your community who maybe haven't heard about this event and encourage them to participate and submit a talk if they can. I know that we had a number of interesting subjects this year that we didn't have last year, like seismic and gravity. So that's the goal going forward, is really to stay on the forefront of what's happening in this industry and keep people informed to continue to have an open discussion so we can all move forward together. I wanted to also say thank you for my time organizing this event. Last year I organized it with Ron Bell and the help of SEG, and this year Laura Quigley and I were organizing this event. So going forward, Laura is taking over as chair of this event, and we are looking forward to having hopefully someone join her. So if you're interested in helping organize this event next year, please don't hesitate to reach out to Lori Whitesell with SEG and Laura. I think both of their emails have gone through the chat at some point recently. And to kind of wrap up, again, thank you to all of our sponsors. We had, I think, 7 or 8 this year, which is just fantastic. And yes, thank you, everyone. This was a great year. Laura, I don't know if you have anything else that you want to add, but I think I've said everything that I intended to say.
No, that sounds great, Morgan. Thanks. Yeah, no, I just want to add, I guess I think we have a really good conference going here. First year was great. This year was even better. And I'm really looking forward to next year. Yeah, so hope to hear from all of you or some of you and new people as well. Thanks, everyone.
Thank you.